Hello, I'm Jaded Company, and we're going to be doing blenders. Gotta love blenders. That music is loud. However, I can turn it down very easily. Just look at this, look at this. There we go. Drop it to about 20. And there we go. We also have to get back because I just posted a YouTube short. I gotta open my I gotta freaking save. Um okay. There we go. File open testament.lib. Okay, so this is where we were last time. We've got ourselves the humane rigging, which we found in the Blender manual. So what I am doing is I am doing my best to learn in a way that is like as authentic as possible because I don't know exactly what I am doing at any given moment. The thing is, I don't want to be like a Blender tutorial person that is just like, yeah, you do this, and doing all the steps. No, no, that's not how people learn. How people learn is you mess around. You have your box of Legos and you just mess around. So is the following things step by step is good when you're building a Lego set. You have that manual and you build the Lego set. But after you've built that Lego set once, you can build whatever you want after that with those Legos. So the problem is that you have to read the manual at least once. And when it comes to all of these other Blender tutorials, it just feels like that they read the manual and then are half trying to explain what's in the manual. In which I'm honestly having more fun reading the manual because then I find gems like this in which humane rigging 14 years ago made these videos. So yeah, we're gonna watch a little bit more of this, and then I'm gonna hop back into Blender and figure out what to do. You know, this is gonna be fun. Maybe I should replay to the beginning of this episode.
The legs, the feet, and the eyes figured out. But what about the body? Or head, or whatever it is? Well, in the case of Mr. Squeegee Feet, his body head thing is really just a big ball. And it really only needs one bone. We want to make sure to orient that bone well so that the local space for it makes sense for the animator. But other than that, there's not much to do. So let's just move right along to putting it all together. First, let's add an armature and put it into X-ray and wireframe display. And turn on axis visualization. Let's make this first bone the body bone. Move the bone a bit below the center of the body sphere, so it will rotate a bit more like hips during a walk. And align it so that the z-axis is pointing up. This way, the up-down translation axis will be the z-axis, just like everything else. Name the bone Body. And now let's add the thigh bones for each leg. thigh.l and thigh.r.
Okay, now this is actually very important because doing the .l and the .r actually is what allows you to do mirroring. Like it doesn't work if you name your bones without .l and .r because then it doesn't do the mirroring thing, doing the same thing on both sides when you turn on mirror. So that is very important and not always explained in the tutorials that I've watched. Or here's the thing, I probably don't pay attention that good in the other tutorials. So that's probably another thing. So
Now, this L and R naming convention for left and right versions of the same
oh
bone
yeah,
is not just for clarity,
yeah.
although it is for that too. But if we name our bones this way, we can take advantage of a cool feature in Blender that automatically keeps bones mirrored across the x-axis of the armature.
Yeah, I'm just re-explaining the video. I'm sorry.
View, there's a checkbox that appears when we're in armature edit mode, labeled x-axis mirror. Turn it on. Now, if we move one of the leg bones, the other stays the exact mirror of it. And this is going to help us set up the armature a lot more quickly, because we only have to do the edit mode positioning for one side. The other side is done automatically for us. Now position the thigh bones to align properly with the model. Select the tip of the thigh bone and extrude to create the shin. You'll notice that even the extrude happens on both sides. Convenient, eh? Now position the shins properly and extrude out the foot bone. Now unparent the foot from the shin, since the foot needs to be free, and make sure to select clear parent rather than disconnect bone. Disconnect bone would only disconnect the bones, but they would still have their parent-child relationship. Now duplicate the foot bone to create a toe bone and place it appropriately. And make the toe the child of the foot. Notice that even parenting is properly mirrored for us. It's pretty cool. Now make the thigh bones the children of the body. And let's duplicate the toe to create the pole target. It's convenient since it's already the child of the foot. Now let's go name all of these bones. Unfortunately, naming is not automatically mirrored, since the mirroring itself is based on the naming, not the other way around. And that's it for the edit mode setup for the legs and feet. Now let's do the pose mode setup. Unfortunately, pose mode doesn't have any mirroring functionality, so we'll have to do everything on both sides. First, add the IK constraints for the legs. Now go and configure them. Set the chain length to 2. And set the pole targets. Adjust the pole target offset. Now lock the IK axes on the shins. And finally, configure the toes with Euler and the appropriate locked axes. That seemed pretty easy, eh? It was really just my long-winded explanations that made it seem complex. Now on to the eyes. Add a new bone for the eye target and position it. Now bones for the eyes and name them I.L and I.R. Position them appropriately. Duplicate them to create the parents, and make the parents a tad smaller. Make the eye bones the children of the parent bones, and parent the parents to the head. Now we're going to turn off X-axis mirror for a moment, because we don't want mirrored duplicates in the next step. Duplicate one of the parents and move it to the middle for the mind's eye. Now name all of these bones that we haven't named already.
Okay.
And go into pose mode and add the damped track and copy rotation constraints. And finally, lock the translation axes on the eye bones. Now we have a largely functional rig, but the mesh still isn't attached. So let's parent all the meshes to the appropriate bones.
Okay, so it's just parenting?
Made bone shapes to the control bones. And we should have done this next bit as we went along, but now let's go and identify the bones that the user never needs to touch and prepend MCH to their names and move them to another layer, because these are our mechanism bones. Strangely, the leg bones themselves are never directly manipulated by the user, so they actually are just mechanism bones. And the eye parents and the mind's eye are also never directly used by the animator. Now we're almost done, but we still have two more things to do that we didn't have to do for the bouncy ball rig. The first is that we need to create a root bone. What is a root bone?
Okay.
A root bone is a big-ass control that moves the entire rig with it. It's a pretty simple concept, and every character rig should have one. It's useful for a number of things, not the least of which is creating offsets for animation cycles. Fortunately, creating a root bone is pretty simple, as long as the various parts of your rig are designed in a way that doesn't sabotage it, and fortunately, ours aren't. So just add a bone at the base of the character, and name it root. Align it so that its z-axis is up, because remember, we want the z-axis to be the up and down translation axis. And finally, simply parent any bone that doesn't already have a parent to it. In this case, that's the feet, the eye target, and the body. Notice that you can parent more than one child at a time to the same parent. Just select as many child bones as you want, and select the parent last. Now if we go into pose mode, you can see that everything moves with the root bone.
Wonderful.
I've also made a custom shape for the root bone, so let's use it. The final step is to sort the controls into different armature layers. When a rig gets complex enough, often the animator doesn't need to use all the controls at the same time, and having them all visible at once can be confusing. Sorting the controls into sensible categories and putting each category into different layers can make rig control visibility a lot easier for an animator to manage. In this case, our rig is still pretty simple, but I think it makes sense to move the secondary eye controls to another layer, since most of the time the animator won't need them, and they obscure the appearance of the eyes a bit. So let's move them to the second layer. Other than that, just turn off X-ray and axis visualization for the armature, and name the armature rig, and we're good to go. Woohoo! Our third rig is going to be a 3D bouncy ball. We're going to take our 2D bouncy ball and bring it into the world of 3D. Sounds simple, eh? And from the standpoint of the actual steps we have to take to rig it, it is going to be pretty simple. Let's cover our requirements for the rig. Just like the 2D bouncy ball rig, our 3D ball is going to be geared towards cartoony motion, so we still need squash and stretch. But unlike our 2D ball, this ball needs to be able to move and rotate in all 3 dimensions. It's still pretty simple. However, in keeping with the pattern of this DVD so far, I'm going to take this simple rig as an opportunity to explain something really complex and weird. And that complex and weird thing is 3D rotations. This is the chapter where you get to learn all about quaternion rotations, Euler rotations, axis angle rotations, and also just about 3D rotations in general. And it turns out that this is a bit of a mind-bending topic, but I'll do my best to make it easy to understand. Wish me luck! Before I dive into Eulers and quaternions and all that good stuff, I first want to cover rotations on a more basic conceptual level. Without thinking about it too much, rotations seem like a pretty simple affair. You have an object, and you can spin it. But in fact, it's not as simple as that. Well, it is that simple, but not all the time. Okay, let me start over by summarizing what I'm about to talk about. There are 2 main things that I want you to get out of this video. The first is the difference between orientations. The second, much more complex 3D rotations are than 2D rotations, and the ways that this affects rigging. So let's start with the difference between rotation and orientation. In short, orientation is where something is, and rotation is how it got there. Or in other words, orientation is a position, and rotation is a change in position. Hopefully that's fairly intuitive right off the bat, but I'm going to give some examples to help illustrate. Imagine we have a wheel with only one spoke. It's not a wheel you would want in your bicycle to be sure, but it's useful for this demo. Now if we spin this wheel by different amounts, that spoke ends up in different positions. The position of that spoke represents the orientation of the wheel. It's just where the wheel is right now. By contrast, rotation is a change in position. If we tell someone to spin the wheel 90 degrees to the right, we're talking about rotation. It doesn't matter where the wheel started, the wheel could have been in any orientation, but the rotation, 90 degrees to the right, is the same in all cases. In computer animation, this distinction between orientation and rotation often gets blurred. And that's because we typically use rotation to specify orientation. We have a neutral starting orientation that we consider unrotated, and then we specify other orientations by applying different rotations to it. Incidentally, it's actually the same with location and translation. Location is just a position. Translation is a change in position. But we specify locations using translations. We choose an arbitrary reference location, and then we specify other locations with a translation vector from that starting point. But you could, if you wanted, apply that same translation to any location. So orientation is like location, it's simply a position, and rotation is like translation, it's a change in position. And if we think about animators for a moment, they're really animating the locations and orientations of objects, not their translations and rotations. But they're using translations and rotations to specify those locations and orientations. Most animators, of course, never think about this distinction, and for the most part, they shouldn't have to. Hopefully, that all makes sense. If not, then
Wonderful.
I failed you, and you should probably ask for your money back. Not that I'll give it back, but you... Well, anyway, moving on.
I didn't pay anybody for this.
Versus 3D orientations and rotations. Let's start with just orientations, since they're simpler and they'll help to lay the groundwork for understanding rotations. So, 2D orientations. They're pretty simple. We can represent the 2D orientation of an object simply with a point on a circle. Wherever that point is, it represents a different orientation in 2D space. Now, if we unwrap that circle, we can see that fundamentally, 2D orientations are actually a one-dimensional affair. They're just a point on a line. It would only take one number, or one dimension, to fully define an orientation in 2D space. Does that make sense? I really want to drive this home. Two-dimensional orientations are a lot like one-dimensional locations. They can only vary in one way, along a line. The only difference is that orientations are on a curved line that wraps back on itself. But the idea is the same. They are both a one-dimensional kind of thing. Kind of weird, huh? So what about 3D orientations? Are they two-dimensional? Well, no, they're three-dimensional, meaning you need at least 3 numbers to fully specify them, which is weird. Or maybe it's not so weird. I guess what's really weird is that orientations in 4D are 6-dimensional, and orientations in 5D are 10-dimensional.
Oh, okay, okay. Okay. Yeah, okay. Yeah. That would be more confusing. That would be more confusing, yes. Just to put it mildly. Why every time the next song plays in the orchestral mix, it changes the volume.
Kind of freaks. Aren't you glad we live in a 3D world? Anyway, all of this is beside the point.
Well, honestly, if we lived in a different dimensional world, we would equally find a 4-dimensional... If we lived in the 5D world, we would equally think that a 4D and a 3D world are equally as incomprehensible, I feel. I feel... Because, like, can you really think about a 2D world that makes sense? I don't think so. Like, how could beings live in a 2-dimensional world? There is no way for things to happen. There's no volume. There's nothing. And 1-dimensional space is just like, friggin' what even is a 1-dimensional space? Like... You can't even comprehend anything living in a 1-dimensional state, much less 2 dimensions. I'm thinking too much. I'm thinking too much.
Is that orientations in 2D space are one-dimensional, and orientations in 3D space are more than one-dimensional. But why does it matter that 2D orientations are one-dimensional and 3D orientations are not? The reason it matters is because of how it impacts 2D and 3D rotations. So here we are now, finally talking about rotations, and this is where the real mind-bending begins. So I've already made the distinction between orientation and rotation, but there is a further distinction to make between 2 different kinds of rotation. The first is what I will call a rotation delta. With rotation deltas, the only aspects of the rotation that we care about is the difference it creates between 2 orientations. Or in other words, all we care about is that this orientation changes into this orientation. We don't care how it got there, We don't care whether it spun this way or that way or how many times it spun around. All we care about is the effect it has on orientation. So spinning the wheel counterclockwise 180 degrees and spinning it clockwise 540 degrees are exactly the same thing as far as rotation deltas are concerned. So that's rotation deltas. The second kind of rotation is what we call a rotation path. With rotation paths, we care not only about the shift in orientation, but also about how it got there. We care what direction it spins, for example, and we care how many times it spins. Rotation paths are important information, for example, if we have two objects connected to each other, like a head is connected to a body with a neck. If the head spins around 1 time, it's going to have a very different effect than if it spins around 20 times. It can also be useful for animating wheels, where we can tell the computer that it starts unrotated, and 100 frames later has spun clockwise 30 times. But why am I calling this a rotation path? All I'm really talking about is preserving the number of revolutions of a rotation, right? Couldn't I just call it rotation revolutions, or rotation spin count, or something like that? Unfortunately, no. There is more to this than just the number of times an object spins around. You can get a hint of why this is by noticing that the direction you spin is important, not just the number of times you spin. And this is where the one-dimensional nature of 2D rotations and the non-one-dimensional nature of 3D rotations comes into play. You see, in 2D, the direction of the rotation is such a simple piece of information, just left or right, that it's easy for us to think of it as a minor thing, just something you tag on to the number of revolutions. But the reason it's such a simple piece of information is because 2D rotations are one-dimensional. It's like giving directions to a person who exists in a one-dimensional world. Hey, how do you get to the bank from here, good sir? Oh, just go right 20 meters. Thank you very much, good man. Ahem. Could you please step aside so that I can pass? I think not. With 3D rotations, however, we have a lot more options. We're not just moving along a single fixed line. We get to choose our line. It's a lot more like giving directions in real life. How do you get to the bank from here, good sir? Head south and take a right on 5th Street, and keep walking until you hit Jackson.
Actually, I think it's faster to head west and take a left on Jackson and keep walking until you hit 5th Street.
Personally, I prefer to take the subway. It goes directly there. I just wander around until I find it. Goodness, multi-dimensional spaces sure are confusing. One of the really sad implications of this is that the concept of revolutions is only meaningful in a limited...
No, but that doesn't... Hold on. But directions are on a... Maps are two-dimensional. Wait, so was he talking about two-dimensional or three-dimensional? The music increased in volume again. Okay, hopefully it stays like that.
Revolutions are predicated on the notion of a single fixed looping path. It's simply the number of times you've traversed that path. With 2D rotations, that's not a problem, because 2D rotations are always a fixed looping path. But in 3D, we have no such guarantees. The path could be anything, and it certainly doesn't have to form a closed loop. And that's why I call this concept rotation paths and not revolutions. Rotations, and in particular 3D rotations, are a lot more complex than that. When animators and riggers want the number of revolutions of a full 3D rotation preserved, they're actually asking the impossible. You have to preserve the entire path of rotation, not just the amount that it rotated. Although, and I'll get to this later, there are some cases where you can preserve revolutions for animation and rigging, although they all rely on predefined rotation paths to a greater or lesser extent. But for 3D rotations in general, it's not always possible. So, to recap, Orientations are where an object is. Rotation deltas are a simple difference or change in orientation, and rotation paths are a full recorded path of how an object rotated to where it is. So after this weird theoretical ride through the topic of rotations, you may be wondering, how on earth is this relevant to rigging? Well, one way that it's relevant is what I noted just a moment ago, which is that the concept of revolutions is really only meaningful in 3D in a limited set of circumstances. Rig controls that rotate freely on all axes, like arms, aren't going to fit the concept of revolutions very well at all. On the other hand, rig controls that have a clear primary axis of rotation, like wheels, are great candidates for revolution-preserving controls because they are much more like 2D rotations. All of this weird theoretical stuff also strongly influences what rotation representation we choose for different rig controls. Some rotation representations, like Euler rotations, have very clear rotation paths. Other rotation representations, like quaternions, are much more like rotation deltas and don't care about the rotation path. And these differences between rotation representations will inform which rotation representation we choose for each control. Lastly, understanding all of this weird theoretical stuff will better equip us to work around or even exploit some of the behaviors and properties of 3D rotations, as well as better inform us. So, let's move on to the real meat of this topic, the different rotation representations available to us in Blender. Blender has 3 rotation representations that we can choose from as a user: axis angle, Euler, and quaternion. Internally, Blender also uses rotation matrices. These are not directly accessible to the user, so I won't go in depth into them, but I'll briefly touch on them at the end of all of this. Of the 3 of these, quaternions are probably the scariest, and axis angle are probably the simplest. And because of that, I'm going to cover axis angle first, and quaternions last. So, axis angle rotations. You have an object, you specify an axis to rotate around, and an amount to rotate around it, and bam, it's rotated. Holy crap, is that simple. It takes 4 numbers, 3 for the axis, and 1 for the angle, and it couldn't be conceptually simpler. Now, I don't know about you, but when I first learned about axis angle, I thought there must be some hidden limitation in there. Surely, there are orientations that you can't reach with a rotation around a single axis. As it turns out, that's not the case. You can reach any 3D orientation from any other 3D orientation with a single rotation around an axis. Or in other words, given any 2 orientations in 3D space, there is always an axis you can rotate around to get between them. It's pretty much the same thing as saying that given any 2 locations in space, there's always a straight line that can connect them. Rotations around axes are like the straight lines of the rotation path world. In fact, the similarities between straight lines and single-axis rotations go even further. Straight lines are always the shortest, most direct path between any 2 locations, and single-axis rotations are the shortest, most direct path between any 2 orientations. Crazy, huh? So in a lot of ways, axis angle rotations are kind of like simple translation vectors. In fact, the only way they could be more like translation vectors is if directly blending or interpolating between 2 different axis angle rotations resulted in the object rotating on an axis as well. Unfortunately, that's not the case, and you can get some slightly wonky interpolations between some axis angle rotations. It's also worth noting that it defines a very clear rotation path, a rotation around a single axis. And it's a looping path of rotation, which means that revolutions are meaningful. Hooray!
Okay.
However, as elegant and simple and awesome as axis angle is, I've never actually used it. If I ever have to animate an entire asteroid field, I might, but as of yet, most of the problems I've run into have been better suited to Eulers and quaternions. And therefore, let's move on to Eulers. Euler rotations are pretty much the most common rotation representation you'll see in most 3D animation packages. In a nutshell, Euler rotations are just a sequence of 3 rotations, one around each of the major axes. So, for example, you might rotate around the x-axis 20 degrees, then the y-axis 90 degrees, and then the z-axis -40 degrees. By rotating around the major axes one at a time, we can rotate the object into any orientation we like. And because we're just rotating around each of the three major axes, Euler rotations are fairly easy to grasp conceptually. Eulers also preserve revolutions around each axis, because each of the three rotations have a well-defined looping rotation path. However, as conceptually simple as Eulers are, in practice, they have a long laundry list of gotchas. The biggest gotcha is something called gimbal lock. But to understand gimbal lock, we first need to cover a different gotcha, which is that the meaning of the Euler axes actually change with different rotations. To better explain this, let's switch over into Blender and take a look at how Eulers work on this monkey head. In the N panel, we can see the three angles for rotating around each of the three axes. If we play with the X value, the monkey head rotates around the X-axis. Likewise, if we play around with the Y value, the monkey head rotates around the Y-axis. And the same with the Z value and the Z-axis. And if we play with the values in sequence, first X, then Y, and finally the Z, this behavior still holds true. However, if we now go back and play with, say, the X-axis, what the? It's not rotating on the X-axis anymore. What's up with that? The reason this happens is because we're doing rotations in sequence. Later rotations in the sequence affect the axes of the earlier rotations in the sequence.
Oh, okay, I don't like that.
Looking device here. As you can see, we have three rings, each smaller than the last, with the monkey head in the middle. Each ring represents one of our Euler rotation axes. The innermost one is the X-axis, the mid-sized one is the Y-axis, and the outermost one is the Z-axis. Now, let's play with these axes individually. Playing with the X-axis, we can see the innermost ring rotate. Playing with the Y-axis, we can see the mid-ring rotate. But notice that it's taking the innermost ring.
Oh.
Finally, playing with the Z-axis, we see the outermost ring rotate, and it takes both of the inner rings with it. It turns out that this is exactly what happens with Euler rotations, and that's why the X-axis was weird earlier.
Oh, jeez.
And then play with the X-axis is no longer aligned with the world's X-axis. However, note that it is aligned with the object's local X-axis, and I'll come back to this later, but just notice it for now. Anyway, the point of all this is that the meaning, or alignment of the axes, change in Euler rotations, so it's not as straightforward as a lot of people think.
Okay, so it's...
Changing axes also mean that interpolation...
So it's local versus global rotation axes.
Between different orientations can be kind of wonky sometimes, which can be annoying for animators to deal with. So, that's the first gotcha. The second gotcha, which I mentioned briefly before, is a direct result of the first gotcha. It's called gimbal lock. What is gimbal lock? Gimbal lock is something that happens in three-axis Euler rotations, where the innermost ring becomes aligned with the outermost ring. This is actually really easy to accomplish. Just rotate the mid-ring 90 degrees. When the middle axis is rotated 90 degrees like this, we have essentially lost an axis of rotation because two of the axes are now exactly the same. This can result in some pretty strange behavior, especially with rotation interpolations, and animators generally ought to be aware of this possibility when animating, and try to avoid rotations that get close to gimbal lock. So that's the second gotcha. Now there is one final thing you want to know about Euler rotations, and that's rotation order. You see, Euler rotations don't have to rotate on the x-axis first. You can choose any order you want to rotate around the axes. We could rotate on Y, then X, then Z, or Z, then Y, then X, or whatever. Blender has a simple way to choose this. In the rotation mode menu, you see a bunch of Euler options. The X's, Y's, and Z's next to each of those indicate the rotation order from left to right. So for example, ZXY Euler means an Euler rotation that rotates on the Z-axis first, then the X-axis, and finally on the Y-axis. This ability to choose the rotation order is actually really helpful. For example, it lets us choose which axis can create gimbal lock. Remember that the mid-ring, when rotated 90 degrees, or negative 90 degrees, or whatever, creates gimbal lock. So if we know there's an axis that will frequently hover at around 90 degrees, we probably don't want it to be the middle axis. Also, remember that I mentioned that the innermost ring stays aligned with the local axes of the object? Well, that means that if there's an axis that would be particularly convenient to stay aligned with the object's local space, you should probably make that the first axis. And similarly, if there's an axis that would be good to stay world aligned, make it the last axis. Just remember that the first axis is like the innermost ring, and the last axis is like the outermost ring. The downside to rotation order is that it completely changes the nature of the shifting axes, which can make things even more confusing for animators. And generally speaking, that means that animators ought to be aware of these issues. A couple of final notes about Eulers. First, if you have one of the axes locked, so that you're only rotating on two of the axes, then Eulers are much better behaved. A lot of the nasty behaviors of Euler rotations, such as gimbal lock, come from rotating on all three axes. So if you only need to rotate on two axes, simply lock one of the axes, and a lot of Euler's rotation problems will disappear. Second, if you only need to rotate on a single fixed axis, like with wheels or something like that, then Euler rotations are pretty much ideal, because then it's essentially just a 2D rotation. Simply lock all but one of the axes. Anyway, so that's Eulers. They seem simple, but in fact there's a lot of complexity and potential for confusion in there, so beware. Now, finally, it's time to talk about quaternion rotations.
Oh no!
As I mentioned in the last video, Eulers are really simple conceptually, but in practice, they're often complex and confusing. By contrast, quaternions are conceptually confusing, but in practice, they are shockingly simple and gotcha-free to use. But indeed, explaining how quaternions function on a technical level is going to be a little bit tricky, so bear with me. I'm first going to give a quick overview of some of the benefits of quaternions and why I like to use them in my rigs. Then I'm going to give a technical explanation of how quaternions represent rotations. And finally, at the end, I'm going to give you a simple, intuitive mental model of quaternions that I use when I'm animating. So, what's so good about quaternions? Well, first I'm going to tell you one circumstance where you never need to use quaternions: single-axis rotations. There's no reason to ever use quaternion rotations for controls that only ever rotate on one fixed axis. It's pointless. For those, use Euler rotations. And similarly, for two-axis rotations, Eulers are often a good choice as well. But where quaternions really shine is with full three-axis rotations, and here's why. First, no gimbal lock or changing axes, which is an issue for Eulers. 2. Rotation interpolation is smooth and direct, which is often not the case with Eulers in the general 3D case. And 3. There are several things that are trivial to calculate using quaternions that are a pain to calculate with other rotation representations, and these are things that are actually useful for rigging. Points number 1 and number 2 are directly related to each other, and I usually think of them as being the same thing. When we rig full three-axis rotations using Eulers, we have to be careful about what rotation order we pick to minimize the possibility of gimbal lock situations and strange axis changes. By contrast, quaternions never have gimbal lock issues and always interpolate between rotations in a consistent way. Recall that when I was discussing axis angle rotations, I mentioned that for rotations, the equivalent of a straight line, the most direct path between two positions, is a rotation around a single axis. Well, it turns out that interpolating between two quaternions always takes this straight line path. And moreover, the nature of quaternions means that whatever interpolation scheme we choose, be it linear, Bezier, or anything else, it will behave consistently and predictably when interpolating. And this is no coincidence. Quaternions represent 3D rotations not as a rotation path like Euler's do with a sequence of rotations, but instead, as we'll see in a moment, represent them more like a rotation delta. And that gives them very stable, consistent interpolation properties because they're not backtracking through some arbitrary rotation path that has nothing to do with what the animator is animating, which is precisely what happens with Euler's. Due to the way quaternions represent rotations, it's also trivial to find the opposite of a 3D rotation, which we'll be using to rig the 3D ball, and to find the minimum angle or distance between two orientations. Both of these are useful to be able to do in rigging. So there we have it. Those are pretty much the advantages of quaternion rotations. But how do they actually work? What do those numbers mean? The first thing that usually throws people off about quaternion rotations is that they have 4 numbers instead of just 3, typically written as W, X, Y, Z. People usually wonder, what does that 4th number, the W, mean? Well, the answer is that it means the same thing as the other 3 numbers. That's not a very helpful answer.
Wait, what?
There isn't anything special about the W. X, Y, and Z have the same bizarre meaning. The only difference is that we consider 1, 0, 0, 0 to be unrotated. But we don't have to. We could consider 0, 1, 0, 0 unrotated, and then X would be the special number. Okay, so this is probably pretty unhelpful so far.
Yeah, no shit.
Understand that there isn't some special different meaning that W has compared to the other numbers. It's not like axis angle where W is the angle and X, Y, Z are the axes. No, with quaternions, all of the numbers do the same kind of thing.
Okay.
What do they do? To explain that, I'm going to show how quaternions work in 2D just for 2D rotations. The way they work in 3D is just a simple extension of that. So the basic idea is this. With Euler and axis rotations, we specify angles, right? Say our starting orientation is here. Then a rotation of 45 degrees would put it here. And that only takes one number to represent. One simple number, the angle. But remember back when I was explaining orientations, I pointed out that we could represent them with a point on a circle. Now, bear with me a moment because I'm about to explain something that's not quite right, but it's a stepping stone to understanding quaternions. Don't worry, I'll correct myself momentarily. Okay, so quaternions basically do exactly that. Instead of specifying an angle, we give coordinates of a point on a circle. So for example, say our vertical axis is W and our horizontal axis is X, and we plot points as WX. Then unrotated would be 1, 0 up at the top of the circle. 90 degrees would be 0, 1 at the side of the circle, and 45 degrees would be approximately 0.7, 0.7 on the upper right of the circle. So you can see that this isn't actually that hard to understand. Although this isn't quite right. Quaternions do something really, really close to this, but not quite. So here's the correction. What quaternions really do is they take the angle you would get from the system I just described, and they double it. So for example, instead of 45 degrees, you get 90 degrees, and instead of 60 degrees, you get 120, and instead of 180 degrees, you get 360. So this is a little bit confusing, but you can get the hang of it with some practice. Just imagine where the point would be on a circle, and then double the angle you would get from that. So let's try it out in Blender. We have this monkey head, and its rotation mode is set to quaternion. As we rotate it on one axis, say 90 degrees, we see that the values relevant to that axis shift approximately to 0.7.7 as we predicted, because 0.7.7 is 45 degrees when plotted on a circle, and the double of 45 degrees is 90 degrees. And as we approach 180 degrees, the axes shift to 0, 1, also as we expected. And this works for the other axes too. And I can take this even a step further. On another layer, I've set up a weird little rig. All it does is take the location of this empty and plug it into the quaternion values of the monkey head. As I move the empty around, you can see that the monkey head rotates twice as much as the angle the empty creates. Wild, eh? Okay, so that's all well and good for 2D rotations, but how does it work on multiple axes for 3D rotations? Well, when we're only rotating on one axis with 2 numbers, the quaternion is a point on a circle, right? where this is unrotated, and this is rotated 180 degrees. When we're rotating on two axes with three numbers, the quaternion is a point on a 3D sphere, where this is unrotated, this is 180 degrees around the x-axis, and this is 180 degrees around the y-axis. And everything else is smoothly blending between those rotations. For example, this point, halfway between these 2 points, represents the orientation exactly halfway between 180 degrees on x and y. And this point, equally distant from all three of these points, is a precise average blend between them. Looking at this, you can start to get a feel for why quaternions interpolate so nicely. And finally, when we're rotating on all three axes with four numbers, well, human intuition falls apart a little bit because the quaternion is now a point on a four-dimensional sphere. But don't worry, the mechanics are exactly the same as the single axis and two-axis case. It's just extended to one more axis. All the same rules still apply. So you may be wondering, why do quaternions double the angle? Why not just leave it alone? Well, let's take a look at the two-axis three-number case again. What would happen if these 2 points represented 90 degrees around the x and y axis instead of 180 degrees? Specifically, what 2 points would represent 180 degrees around x and y? Well, let's try x first. Intuitively, we would just keep following the circle to the bottom of the sphere, right? Okay, cool. So that point now represents 180 degrees around x. Now what about y? Well, let's follow this circle down to... Oops. The bottom of the sphere. The bottom of the sphere appears to represent both 180 degrees around x and 180 degrees around y. But that doesn't make any sense at all. If you rotate something 180 degrees around x or 180 degrees around y, you would get very different orientations. So we need them to be different.
Ah, okay.
Between 180 degrees, then following these circles gives us 360 degrees around x and y at the bottom. And guess what? Rotating something 360 degrees around x or 360 degrees around y results in the same orientation. So it works out. And this doubling of the angle actually has a side benefit. Quaternions can represent 720 degrees of rotation, not just 360. This property of quaternions is commonly referred to as double cover, and it allows us to do things like find the opposite of a rotation in W negative.
Sorry. That's the alarm that I typically have to go to work.
And one here, but it's interpolating the wrong way. He can simply flip all of the components of one of the quaternions, and then it will interpolate in the other direction. One last thing to note is that technically speaking, quaternion rotations are only defined for points that are precisely on the surface of the sphere. Or, to take a look at the 2D case again, if we put a point out here, it doesn't count. Only points that are exactly on the circle count. This is one of the reasons that a lot of software, like Maya and Softimage XSI, choose not to expose the actual quaternion components to the user. If the user can freely manipulate the quaternion coordinates, then they can put the coordinates in all kinds of illegal places. Blender, however, does directly expose the quaternion components, which I think is kind of nice, and what Blender does for coordinates that are not exactly on the circle, or sphere, is it interprets them as if they were projected onto it, like so. The only point this doesn't is 0, 0, 0, 0, in which case it defaults to some weird orientation, which isn't really a big deal since you never hit 0, 0, 0, 0, unless you're intentionally trying to. So there is actually one reason why a lot of software doesn't directly expose the components of quaternions, and that's because of something called slurping and squatting. What on earth are those? Those are kind of weird names for stuff.
Yeah.
Well, remember how quaternions always rotate on a single axis if you interpolate between just two quaternions? Well, a slurp, or spherical linear interpolation, is a further restriction on that, where not only does it rotate on a single axis, but it does so at a constant angular speed. It turns out that the math for this for quaternions is pretty straightforward.
Okay.
A squad is something similar, it's just that it's for a smoother interpolation, quite a bit like Bezier interpolation. Unfortunately, enforcing proper slurping and squatting requires that the software limit certain things about how quaternions work, and these are limitations that cannot be enforced if the actual curves of the quaternion components are exposed in the animation curves editor. And This is another reason why, for example, Maya and XSI do not let the user directly tinker with quaternion components. It gives the software a chance to do these nice types of interpolation. Blender takes a different tactic, which in my opinion is a better one, and just uses the typical interpolation techniques to directly interpolate the quaternion components. This gives the user free rein to control how their rotations are interpolated, but it also has a drawback. Let's revisit the 2D circle once more. Let's say we're trying to interpolate between this angle here and this angle here over the course of 5 frames. A slurp would do a nice constant speed interpolation over the part of the circle between them, but a straight linear interpolation of the coordinates, after being reprojected back onto the circle, would be a bit slower towards the beginning and end, and faster in the middle. This is the drawback to exposing the quaternion curves and interpolating them directly. However, notice that this is really more of a problem for interpolations between very different rotations than it is for rotations that are closer together. In fact, even for rotations as large as 90 degrees, remember quaternions double the angle, the issue is hardly there at all. So in practice, this usually isn't a big deal. The animators simply insert 1 or maybe 2 additional keys for large rotations. So this is all well and good. Quaternions are pretty cool. But there is a downside to quaternions, which is that they are generally harder to grasp conceptually than Eulers. This isn't such a problem for us riggers, who only deal with quaternions on a technical level anyway, but for animators, who should be focusing on the art and not the tech, it can make quaternions quite intimidating. Fortunately, there are a couple of ways to help animators out with that. The first is to tell animators to just ignore what quaternions mean and just treat them as some abstract representation of rotations. This is actually how I worked with quaternions when I was animating on Big Buck Bunny. Instead of worrying about tweaking animation curves and all, I just set extra rotation keyframes to define things like ease in and ease out and sharp changes in rotation speed and direction. And because of how nicely quaternions interpolate, this actually works out really well. The other way, which I use now, is to think of quaternions as mixing orientations. Kind of like color, where we're mixing red, green, and blue, except in this case we're mixing 4 orientations. One that's unrotated, one that's rotated 180 degrees around X, one that's rotated 180 degrees around Y, and one that's rotated 180 degrees around Z. But the principle is basically the same. The hue of a color is determined by the ratio of red, green, and blue in it. 1 part red and 1 part green makes yellow, and 2 parts red and 1 part green makes orange. Similarly, the orientation of a quaternion is determined by the ratio of the 4 core orientations we mix in. 1 part W and 1 part X is an equal mix of W and X, so the orientation is exactly halfway between them. 1 part W and 3 parts X has a lot more X in it, so it's going to be closer to X. What's great about this mental model of quaternions is that it's actually extremely close to how quaternions really work. The only thing it doesn't account for is what negative values mean. But that's easy to tag on to the mental model. Negative values merely rotate the opposite direction when you mix them in, but they're still mixing towards the same orientation. They're just going the other way around to get there. And in fact, that gives a really good intuition for why flipping a quaternion, or in other words, flipping the negative signs of all of the components, will make it interpolate the opposite way around. It's because all of its components are mixing in the opposite rotational direction. Anyway, so yeah, that's the mental model of quaternions that I use when I'm animating. I think of quaternions as being like mixing 4 different colors of paint together, except instead of colors, it's mixing orientations in space. And honestly, in a lot of ways, quaternions are more artistic to me than Eulers do, because it's like mixing paint. Yeah. So the last thing I want to touch on before we get back to actual rigging is something called transform matrices. A transform matrix is a 4x4 grid of numbers that represents everything about the location, rotation, and scale of an object. Not only that, but transform matrices can also represent things like shear. Basically, they're the mother of all transformation representations as far as flexibility goes. However, like quaternions, the rotation part of transform matrices don't have a concept of rotation path. They're much more like rotation deltas. In fact, transform matrices are even more like rotation deltas than quaternions are, because unlike quaternions, which cover 720 degrees of rotation, transform matrices only cover 360. I won't go into the math of transform matrices, but you should be aware that Blender uses them internally for representing and manipulating object transformations. When you, as a user, specify the location, rotation, and scale of an object in the N panel, or when those values are generated by animation, Blender actually converts them into a matrix for all.
I forgot to grab my tea. Again, I forgot to grab my tea. Thanks for getting my tea. I eat my breakfast, and then I forget about drinking fluids. There we go.
All of its internal object manipulations. For example, parenting and constraints are both accomplished via transform matrices in Blender. Even armature deformations are based on the transform matrices of bones, not the values you specify in the N panel. This is important to know because later on, it will explain some behaviors that might otherwise seem kind of weird. So with that out of the way, let's finally get back to rigging. So, here we are again.
Wonderful.
With a ball staring right back at us. It wants us to rig it, I can tell. Let's not disappoint. Most of the steps for this are going to be the same as rigging the 2D bouncy ball. The only real difference is that we're going to be using quaternion rotations instead of Euler rotations. However, a lot of the animation that might be done with this ball may still move along a more or less 2D path, so we don't want to prevent the animators from using Eulers, because sometimes it may be useful. If you recall from the 2D ball rig, we're going to use 3 bones, 2 of which will be controls. We'll have a control for location and squash and stretch, and we'll have a control for the spin of the ball. The squash and stretch control needs to rotate to determine the direction of the squash and stretch. We'll be using quaternions for that. But the spin control we'll leave up to the animator. They can select their preferred rotation mode from the drop-down menu. So, let's get started. Add an armature, and set it to X-ray and wireframe display, and turn on bone axis display. Name the armature rig. Go into edit mode, and name the default bone main. And adjust its position so that its local axes line up with the world axes, so that the local axes will behave as the animator expects. Now duplicate the main bone to create the counterspin bone, and position and name it appropriately. And make it the child of main. Now go into pose mode. We need to set up the counterspin bone to do the opposite rotation of the main control. Since the main bone is using quaternions for its rotation, this turns out to be pretty easy. Remember that quaternions cover 720 degrees of rotation, so both the top and bottom of the circle are effectively unrotated. So flipping the W component makes the quaternion do the opposite rotation. And happily, this works in the full 3D case as well. So to make the counterspin bone do the opposite rotation, we're going to drive its quaternion components with the quaternion components of the main control. X, Y, and Z will simply be copied, but the W component will be set to the negative of the main control's W component.
Nice.
Let's start with X. Add a driver to the counterspin bone's X component. And let's go to the driver's interface to configure it.
Graph drivers. Quaternion rotation.
Remember that drivers have two parts, variables and what is done with those variables. To drive the X component properly, we need direct access to the X component of the main control's quaternion rotation. You might think we could just select X rotation in a transform channel variable, but you would, unfortunately, be wrong. Remember that Blender uses transform matrices internally? Well, the transform channel variable type derives its information from transform matrices, translating them back into some kind of Euler rotation. So if we used this, we would be driving the X quaternion component with an X-axis Euler rotation, which is clearly not the same thing. Instead, we need direct access to the quaternion component of the main controller. There is a variable type that lets us do this. It's called single property. This variable type allows us to access any user-accessible piece of data in Blender via something called RNA paths. Blender stores this data in something called an RNA system. It's kind of like the file system on your computer, where you have file paths, and different pieces of data are stored in different files.
Okay, cool. I understand that.
We first need to specify what object it's inside. In this case, that's our armature. Select it in the field here. Now we need the RNA path relative to that object. The syntax is very different from file paths on your computer, but the idea is basically the same. Thankfully, you don't actually have to learn the syntax. Select the main bone, right-click on any of the quaternion components. Towards the bottom of the menu, there's an item called Copy Data Path. Clicking on it will copy this property's RNA path into our clipboard. Click it. Now go back to the driver. We can now paste the RNA path into the path field with Ctrl-V. If we expand the panel a bit, we can see the full path. However, this is not all we need to do. This path references the entire quaternion, but we need a specific component of it. Thankfully, we can just put .x at the end to get the x component. Awesome. Now this variable is equal to the x component of the main bone's quaternion. You can access nearly any piece of data in Blender in your drivers this way. Now we just have to use this variable in the driver itself. We could type in the variable name in the expression field, but a simpler way when the driver is just going to directly use the variable is to change the driver type to some values. This is basically like a shortcut that just adds all of your variables together. When you only have one variable, that means it's just going to copy it. Average value is similar, except it calculates the average value of all the variables. Minimum value and maximum value take the minimum or maximum value of the variables. It's all pretty straightforward.
Okay.
All of these things could be achieved with scripted expression, if you wanted to, but these are simple shortcuts for common cases. In any case, let's select some values, and click Update Dependencies. Now if we rotate the main bone a bit, and select the counterspin bone, we can see that it's copying the x component of the main bone's quaternion. Yay! Now, we could go through this whole process over again for each of the quaternion components, but there's an easier way when you need to make a lot of very similar drivers. Right-click on the counterspin bone's x quaternion component. There's an item labeled Copy Driver. Click it.
Okay.
Now right-click on one of the other components, and select Paste Driver. Ta-da! The Y component now has exactly the same driver. Of course, we don't want it to be exactly the same. Right now it's copying the X component, but that's easy to change. Paste the driver on the other components. Now we just have to change the RNA paths. And update the dependencies on all of them. Now if we rotate the main bone, the counterspin bone rotates in the same way. Of course, since it's the child of the main bone, that appears as a double rotation. But we don't need a double rotation. We need the rotation to be countered. So go to the W driver, change it back to scripted expression, and enter the negative of the variable to flip the W component. Now if we rotate the main bone, the counterspin bone doesn't rotate at all. Yay! Now let's set up the squash and stretch. It's the same as in the 2D bouncy ball, just be mindful of the axes.
Maintain volume on the main bone. X, Y.
We also need to make sure that the animator doesn't change the rotation mode of the main control, since our counterspin bone depends on it using quaternion rotations. There's no lock button next to the rotation mode menu, but there's a cool trick you can use to lock any field you want. Add a driver. And now change the scripted expression to be 0. Each item in the rotation mode menu has a corresponding number. 0 is the number for quaternion. Now we can't switch the rotation mode away from quaternion. Finally, it's time to add the spin control. Add a new bone, and position and name it appropriately. And make it the child of the counterspin bone. And make the ball the child of the spin bone. We now have a basically finished 3D ball rig. However, notice that the spin control behaves a little bit oddly when there's an extreme squash and stretch. This is because Blender doesn't handle distorted controls very well. So what we really need to do is have an undistorted control that our current spin control copies its rotation from. This means that our current spin control isn't actually going to be the control anymore, so let's rename it to be a mechanism bone. And let's add another bone and name it spin, and position it appropriately. The difference is we're not going to make it the child of anything, because we don't want it to be distorted during squash and stretch. We still want it to stay in the right position, however, so let's constrain it to copy the location of the counterspin bone. This way it will stay at the center of the ball. Now we need to make the spin mechanism copy the rotation of the spin control. We can do this with a simple copy rotation constraint. So let's give this a try now. Stretch the ball and play with the new spin control. Oops.
Oh.
That doesn't seem to work. It's rotating the squash and stretch as well. What's going on? Let's take a look at the copy rotation constraint again. Notice the two menus at the bottom of the constraint? These menus determine what space the constraint operates in. Right now it's operating in world space. What that means is that no matter what a bone's local space is, it will still snap exactly to the same position as the other bone. If we switch this to local space though, then the local space rotation of the bone will copy to the local space rotation of the other bone. Let's take these two bones as an example. They are currently in zeroed out positions. If we add a copy rotation constraint between them, the one bone snaps to the exact same orientation as the other, despite their different spaces. But if we change the space of this constraint to local, now the bone is copying the rotation relative to its local space.
Okay.
We can do something similar. The reason we get the weird result with the copy rotation is because it's doing the copying in world space, which is outside of the distorted stretched space. But if we change it to local space, then it does the copying inside the local distorted space of the bone, and it works as we expect. And notice that this new control doesn't have the weird behavior of the distorted control. Hooray! One thing you may be wondering is why there are two menus for the space of the constraint. The reason for that is because the left one says what space we're copying from, and the right one says what space we're copying to. So if we wanted to, we could, for example, copy the world space rotation of the spin bone into the local space rotation of the mechanism spin bone. That might not seem useful, but being able to choose those two spaces separately can be handy in some corner cases that would otherwise be a pain to deal with. Anyway, now the functionality of the rig is done. We just need to assign the control shapes. Let's move the mechanism bones to their own layer. And I've already created the shapes. So let's assign the main control bone shape. And then the spin controls shape. Oh my, that's a little bit too big. Let's go and edit the mesh to be the right scale. Oh, and we need to lock the location and scale of the spin control. It's only for rotation, right? And let's turn off X-ray and axis display on the armature. Now let's test. Oh my, the spin control doesn't stretch with the ball. I guess that's to be expected, but it doesn't look right. Fortunately, Blender has a cool way for us to make it look right. If you go back to the bone shape panel, you'll notice that there is an at field under the shape field. This field allows us to choose a different bone that the shape will use as its position. The shape will still be for the spin control, but the appearance of the shape will be based on a different bone. It's kind of weird, but it's useful for situations like this. Select MCH spin for the at field. Cool! Now it looks a lot more like the animator would expect. And now, the rig is done! Congratulations! Yay! Say hello to Mr. Hot Dog.
Oh, jeez.
Character. If I weren't vegetarian, I would probably eat him. He's probably glad that I'm vegetarian.
Wait, eat this.
Let's figure.
Okay, this person, they're cool. I'm not gonna lie, they're pretty cool. I like them. I like them. I'm not personally vegetarian, but I love my vegetarians. They are they are correct in a lot of things. I am very hopeful for the future of lab-grown meat, but that's just me personally.
Out our requirements. What is Mr. Hot Dog
Yep.
going to do? Other than get eaten, that is. Well, like Mr. Squeegee Feet, he's going to look around with his eyes. But unlike Mr. Squeegee Feet, he doesn't have legs, so instead of walking, he's gonna hop around. Also, unlike Mr. Squeegee Feet, he does have arms and hands, complete with a few fingers. He needs to be able to swing those arms around, but he also needs to be able to grab onto things with his hands. So breaking it down, we have 4 things we need to figure out how to rig. First, his hands and fingers. Second, his body. Third, his eyes. And fourth, his arms. This is gonna be fun. Let's get started. Fingers are an interesting rigging problem, which can vary a lot depending on requirements. For Mr. Hot Dog's fingers, however, we're going to assume that an FK style rig will be fine, and that the finger digits just need to be able to bend and rotate. But you can imagine that an IK style rig can be helpful in many circumstances, such as typing on a keyboard. The simplest finger rig you could create would be to just add 1 bone for each segment of the finger, and put them in a bone chain. This is certainly workable, and animators can indeed animate this way. However, this requires that the animator manage each segment of the finger individually, which can be a lot of work when we're dealing with a whole hand of fingers. So how can we simplify this? Well, remember that when we designed the leg rig, we started by looking at how legs typically move. That's pretty much the starting point for making any simplified rig, observing how things actually move and function. So let's take a look at how fingers typically move. The main thing I want you to notice is that the second and third knuckles usually bend together in a consistent way. They also typically only bend on one axis. By contrast, the first knuckle can bend independently quite easily, and in fact often does. It also frequently bends on 2 axes. So given that the second 2 joints move together, and basically only move in one way, that means we can easily assign just 1 control to both. In fact,
Can anybody like do one finger at a time? Whenever I try to move my pinky, my ring finger twitches a little bit. But if I really focus on it, it doesn't really. Man, okay. Maybe I should stop embarrassing myself. Okay.
If we wanted, it could be a single number corresponding to the angle of rotation of both joints. However, the first joint needs a more full-fledged rotation control. Still, this simplifies things a lot. Instead of the animator dealing with 3 axes of rotation for 3 bones, they only need to manage 3 axes of rotation on 1 bone, and then a single additional parameter. How can we design the rig to efficiently exploit this, though? One thing that would be nice is if we can make all of this operate from a single control. Ideally, we don't want the animator to have to switch selections to tweak different parts of the finger. It would be much nicer to just have one control per finger. To accomplish this, I'm going to introduce a new concept. Now, using things like drivers, we can make any parameter drive any other parameter, right? So, for example, we can make the scale of one bone affect the rotation of another bone. This kind of mapping from one kind of transform to a different kind of transform can be really useful, since often
Okay.
all of the transforms, location, rotation, and scale, are relevant to a control. If the scale of a control isn't being used directly, why not make it do something else? A word of warning, though. You want to use this kind of thing sparingly, because it can easily reduce how intuitive and obvious and friendly your rig is to use. It is not obvious that scaling a control will cause something else to rotate. It's the kind of thing you have to explain to an animator. And the more of these weird exceptions they have to keep in their heads, the more they have to think about the rig, and the harder it is for them to focus on animating.
Okay.
So doing this kind of thing really needs to be worth it, and you shouldn't do it all over the place. So let's try this out. Let's create a 3-bone chain, and let's switch the armature to wire and X-ray and turn axis display on. And let's name our bones.
Digit 01. Digit .02. And then it's doing digit .03.
Make sure that the bones are aligned in a nice way. I find that it's nice to try to make the primary axis of rotation the same on all controllers. I usually use the x-axis. So, for example, fingers usually bend primarily in one direction, so I want to make that the x-axis. Moreover, let's try to make that direction a positive rotation, rather than a negative rotation. Setting things up this way keeps the controls consistent for the animators when they're working in the animation curves editor. It looks like we're already good as far as rotating on the x-axis goes, but if we bend the finger on the x-axis, the rotation is happening in the negative direction. So let's flip the roll of the bones 180 degrees. We should also probably change the rotation mode of the bones to Euler, because fingers rotate so much on a single axis. Since X is the primary rotation axis, it makes sense for it to be the last axis in the rotation order, so that it stays aligned with the hand, or whatever else we might parent this rig to. And we probably want the twist of the finger, in this case the y-axis, to stay aligned with the local rotation of the finger, so it should probably be the first axis. That leaves the z-axis as the middle axis, which can cause gimbal lock. But since z is the side-to-side motion of the finger, and fingers only rotate side-to-side so much, that's unlikely to be an issue. So set the bones to y, z, x Euler. So now let's add the control bone. To do that, I'm simply going to duplicate the first finger digit. By duplicating the first digit, we guarantee that it is in exactly the same orientation, which we want. Now we can strain the first digit to the control bone with copy rotation constraints. Now if we rotate the control bone, the first finger digit goes with it. So this takes care of being able to rotate the first digit with the control. Now we need to make it so that scaling the control bends the second 2 digits. We really only only need it to scale on one axis, and it looks nicest if it's the y-axis. So lock the other two axes. Now it only scales on the y-axis. Now, there are actually two ways we can make the finger bend when scaling the control bone. One way is to use drivers, but another way we can do it, and the way that we're going to do it, is with something called action constraints. Action constraints are a slightly strange constraint in Blender. Remember how the animation of objects are stored in actions? Normally those actions affect objects based on the progression of time. But with action constraints, we can have actions affect objects based on the transforms of something. What this means for us is that we can simply make the animation of the finger bending, and then have that animation affect the bones based on the scale of our control instead of based on time. So let's try it out. Make sure you're on frame 1, and set a key on the second 2 digits in the unbent position. Now change to 10 frames later on frame 11, and bend the finger, and set keys for that bent position. Now if we scrub the timeline, we can see the finger bend and unbend. Now what we're going to do is take this animation and link it to the scale of the control bone. To do this, we first need to do a little bit of action management.
Wait, hold on.
And change it from dope sheet.
Hold up. How did...
Control instead of based on time. So let's try it out. Make sure you're on frame 1, and set a key on the second 2 digits in the unbent position. Now change to 10 frames later.
Wait. What do you mean set a key?
Try it out. Make sure you're on frame 1, and set a key on the second 2 digits in the unbent position.
Insert keyframe. Oh boy. My brain is gonna be fried. However, I'm gonna have to, after frying it, I need to saute it a little bit, and then toss it a little bit, and then come back later, and then I'll understand it. Taking notes. Things I still need to learn. What is the frickin' keyframes? Things I don't understand.
Now change to 10 frames later on frame 11, and bend the finger, and set keys for that bent position. Now if we scrub the timeline, we can see the finger bend and unbend. Now what we're going to do is we can see the keys for that bent position.
So I did insert keyframes and then insert keyframes.
Now if we scrub the timeline, we can see the finger bend and unbend. Now what we're going to do is take this animation and link it to the scale of the control bone. To do this, we first need to do a little bit of action management. Create a new window and switch it to the dope sheet view. And change it from dope sheet mode to action editor mode. From here we can manage actions as pieces of data. We can see the name of the action on the currently selected object here. Let's rename it to something useful, like finger bend. Also, we want the interpolation to be linear for this. By default, Blender interpolates keyframes with Bezier curves, which creates an ease-in, ease-out kind of effect. But we don't want our controls to automatically do that, because if the animator doesn't want that, they'll have to counter-animate against it. Linear interpolation, on the other hand, will reproduce exactly whatever the animator does. To change the interpolation to linear, make sure all the keys are selected with the A key. They should all be yellow. Then Then press T and select linear from the menu that pops up. That sets the interpolation type to linear for all of those keys. Now let's remove the action from the armature, since we don't want it animating with time. We only want it to animate when we scale the control bone. To do that, click the X here. Now if we scrub the timeline, nothing happens. And now it's time to add the constraints. We need to add an action constraint to each bone that we want to be affected. The control is going to be the constraining bone, so select it first, then the second digit bone, and add an action constraint. Go to the bone constraint properties. We need to specify what action is going to be used. In this case, it's finger bend. And we need to select Scale Y as the transform channel that drives this.
Scale Y.
We're almost done for this bone. We just need to specify the mapping. The action starts on frame 1 and ends on frame 11, so enter those into the action length fields. The min and max fields represent the values of the transform channel that will correspond to the beginning and end of the action. The names are a little misleading because min doesn't actually have to be smaller than max. Just think of min as the value that matches up with the start frame, and max as the value that matches up with the end frame. In this case, we want unscaled to mean unbent. 1.0 is the value for no scaling, so put that in the min field. And let's put 0.5 as the max, so the finger is fully bent when the control is half size. Let's try it out. Scale the control bone. Oh, look at it bend. We could repeat this process for the third digit, but it's easier to simply copy the constraint. Select the third digit, and then the second digit. In the pose menu under Constraints, there's an item called Copy Constraints to Selected. This will copy all the constraints on the last selected bone to all the other selected bones. Click it. Ta-da! Now the third digit has the same constraint. Try scaling the control bone now. Cool. And if we rotate it, the first digit rotates with it. We now have a single comprehensive control to do most of what we want with the finger. How cool.
Wonderful.
Also, one of the benefits of action constraints is that due to the way they work, we are able to animate the constrained bones on top of it without having to do the whole parenting trick. So this way the animator can still tweak the individual digits if needed, which is important because sometimes the animator may need the finger to do other things. But this single control covers most cases and makes those cases a lot faster for the animator to manage. Anyway, that's how we can accomplish this with action constraints.
Okay.
However, the real power of action constraints is when you have a very complex action that you want the animator to be able to easily control. For example, the gears of a jet airplane raising and lowering with lots of complex hydraulics. There's no reason for an animator to have to manually animate that every time. So instead, we could use an action constraint to drive it with a single control. For this finger rig, we could also use and the parenting trick for animating on top of automation. But action constraints are a little bit easier and allow us to use fewer bones. As a last step, let's scale our control bone up and move it to the same location as the first finger digit. Now when we use the control, it feels more direct, like we're really grabbing the finger and moving it around. Next up is the body. So, what do we want the body to do? The main thing is that we want it to be able to bend and twist around without the bottom of the body sliding around. If the bottom slides around when we bend the body, then the animator would have to counter-animate to keep it from sliding, which is bad. As with the finger, the simplest way to accomplish this is just to use a simple bone chain. If the base of the chain is on the ground, then rotations won't make the body slide around. However, a pure FK chain has a different kind of counter-animation problem. If we rotate the bottom of the body, but we want the top to stay in the same orientation, then we have to counter-rotate. For a character like this, there are probably lots of situations where it would be nice to have easy independent control over the rotation of the top and bottom of the body, so this is important to address. Another thing to consider is that for a simple character like this, it would be nice for the middle bones of the chain to automatically form a smooth bend based on the orientation of the top and bottom bone. Doing this would, unfortunately, remove some control from the animator, but it would also make the rig simpler to use and faster to animate with. It's a trade-off, and it's a trade-off that may not be good, depending on what the rig is going to be used for, but let's assume that the trade-off is a good one for this rig. To accomplish these goals, we're going to need to delve a little deeper into constraints. Let's take a look at these two bones here. If we add a copy rotation constraint between them, and rotate this bone, then the other bone follows its rotation. Old news, I know, but here's the interesting thing. It doesn't have to fully copy the bone's rotation. If we go to the bone constraint properties, we see that at the bottom of the constraint, there's a slider called influence.
Ooh,
This
what?
determines how much the constraint affects the bone. It's kind of like an alpha value for constraints. So, for example, if we set it to 0.5, then when we rotate this bone, the constrained bone only rotates half as much. But it gets even better than this. So far, we have only ever added one constraint to a bone, but the constraint system in Blender allows layering of constraints. Let's add a third bone to the armature. And let's add a second copy rotation constraint using this bone. Now in the constraint properties, we can see that there are not just one, but two constraints, one on top of the other. This is called the constraint stack. Constraints in the constraint stack affect objects and bones in top to bottom order. So this constraint is applied to the object before this constraint. So as things are right now, the first constraint makes the bone copy the rotation of this bone halfway, and then the second constraint makes it copy the rotation of this bone completely. In other words, right now, the second constraint is completely overriding the first, because the second constraint has full influence and is placed later in the constraint stack. But let's try changing this. Set the first constraint to full influence, and set the second constraint to half influence. Now if we rotate the bones, the constrained bone stays exactly halfway between the rotation of both. This is because the first constraint puts the bone in the same rotation as our first bone, and the second constraint then rotates it halfway towards our third bone. Now if we leave the bones rotated, and we play with the second constraint slider, we can see the effects more clearly. When the slider is at 0, the bone copies the first bone entirely. This is because the second constraint now has 0 influence. It might as well not even exist. But as we slide the influence towards 1, the constrained bone rotates towards the third bone, copying it entirely when we reach 1. It's just like alpha values in image editing. Just remember that the stack starts at the top and goes to the bottom, not the other way around. If you want to move where a constraint is in the stack, you can use the up and down arrows here. Something else to be aware of is that some constraints don't really interact with each other. So for example, if we add a copy location constraint, the rotation constraints don't get overridden. Only constraints that affect rotation will override them. This is important because otherwise, we wouldn't really be able to constrain both the location and rotation of a bone or object. We could only use one or the other. The last thing to note about constraints is to reiterate that they use transform matrices and do not affect the transform values in the end panel. These transform values are turned into a transform matrix, and that matrix is then fed into the top of the constraint stack, getting modified by each constraint in turn, and it's finally spit out at the bottom as the final transform matrix of the object. One way that this matters to us riggers is that because matrices only represent 360 degrees of rotation, rotation constraints with partial influence can cause flipping when you hit 180 degrees. There isn't really any way for the constraint system to know which way around you want the bone to blend, so it always just picks the shortest route. Another way that this matters to us as riggers is that because the matrix is created from the transform channels, constraints are almost always applied after drivers, since we need the driven transform values to construct the transform matrix. There are a very few exceptions to this, but as a general rule, this is true. So let's apply these lessons to create a nice body rig for Mr. Hot Dog. The goal here is to constrain the two middle bones to be a blend of the rotation of the first and last bones. But there's a gotcha in there. To constrain the middle two bones like that, they need to partially copy the rotation of the last bone. But the rotation of the last bone is affected by the middle two bones due to the parent-child relationship. This is called a cyclic dependency, because this bone's rotation depends on that bone's rotation, but that bone's rotation depends on this bone's rotation. It's a cycle, it's like a paradox, it's unsolvable. So what we need to do instead is create another bone that's entirely outside of this parent-child hierarchy, and that will be the control for the top of the body. Then we can have all three of these bones influenced by it. Similarly, we're going to create a separate bone to be the control for the bottom of the body. This isn't strictly necessary because using the base bone directly wouldn't actually create any cyclic dependencies, but I like to do it this way for consistency. So let's do that. Add two more bones with the same orientation. And now let's make sure that all of the bones are aligned the same way, because otherwise in the default pose, the constraints might actually cause some rotations. Looks like they aren't really aligned, so let's roll them into place. Now, the top and bottom bones of the chain really just need to directly copy the rotation of their respective controls, so just use a single copy rotation constraint for each. If we rotate the controls now, we can see the effect that this has. Now constrain the middle two bones to the bottom control with copy rotation constraints. Again, this isn't strictly necessary since they follow its rotation due to the parent-child relationship anyway, but I like to do it this way. Next, constrain them to the top control. Now if we play with the controls, the situation sort of looks reversed, with the middle two bones following the top control instead of the bottom. Leave the top control rotated, and now select the third bone in the chain, and go to its constraints. We can now tweak the influence of the second constraint to get the blend we want, and since we left the top control rotated, we can directly see the effect that this tweaking is having. And we can also do the same thing for the other bone. And in fact, we can just go back and forth, tweaking both, until we get something that we're happy with. That seems fine. Now what happens when we play with the controls? Ooh, fun! We can control the rotation of the top and bottom independently of each other, and the middle bones automatically bend smoothly to accommodate that. However, something that would be even cooler than this would be if the controls affected all of the transforms. Right now, the only thing that's affected is rotation, but what if we could scale the bones too, and have it blend nicely as well? For that, I'm going to introduce a new constraint. Delete all the constraints we already have.
Oh, okay.
Now we want to do the same thing as before, except instead of using copy rotation constraints, we're going to use copy transform constraints. Notice that the bottom bone immediately snapped to the bottom control's position. That's because the copy transforms constraint doesn't just copy rotation, it also copies location and scale. In fact, what it actually does is it just makes an exact copy of the other bone's transform matrix, which means it also copies things like shear as well. In any case, it's pretty confusing having the control and bottom bone overlap exactly, so let's scale the control up a bit in edit mode. And let's do the same for the top control as well. And other than that, just follow the exact same process as before, just using copy transforms instead of copy rotations. One thing to notice is that the copy transforms on the other bones don't snap them to the same location as the constraining bone. That's because they're in a connected chain, and therefore are unable to move away from their connected locations, even with constraints. In this case, that's exactly what we want. But if we didn't want that, we could always disconnect the bones. Now let's play with this. Cool. Now the scale gets nicely blended across the chain as well. Which means if the animator wants, they could actually do some kind of squash and stretch with this rig. There are just two more things to do. First, we don't really want the top control floating out in the middle of nowhere. We want it to move with the body rig. So let's constrain its location to the bottom control. Second, we don't want bones to move from their default positions unless the animator has moved them. So let's place the bones in edit mode such that they stay put even with the constraints applied. And we're done. When we create this for the final rig, of course, we'll give the controls shapes that make this less visually confusing. But as far as the mechanics of the rigging go, we've got a pretty nice thing going on here. Eyes, the window into the soul. Blah, 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 blah. Okay, yeah, we've been over this already.
Yeah.
Mr. Hotdog's eyes, pretty much exactly like we rigged Mr. Squeegee Feet's eyes. So go back and watch that video again if you've forgotten. But we're going to make a couple of improvements, starting where we left off with Mr. Squeegee Feet's eyes. The only thing I've added here is a head bone with the appropriate bones parented to it, which is going to be important for one of the things we're going to do. The first thing we're going to do is address a simple shortcoming in the iRig's user interface. As it is right now, if the user wants to cross the character's eyes, they need to manually rotate the secondary eye bones. That's kind of annoying, especially considering that crossing your eyes a little is actually a common thing to do, for example when you're looking at something near your face. So it would be a good idea to give animators a shortcut to be able to do this easily and quickly. To do that, we're going to use the same technique as we used for the fingers.
Okay. Action constraint, scaling, and then it's rotation, but you have a copy rotation for a negative value on one of the eyes. Is that what's gonna happen?
What we need to do is make an animation of the eyes crossing and link that to the scale of the eye target with action constraints.
Okay.
So let's make the animation first.
Oh.
Make sure you're on frame 1 and insert keys on both of the eye bones. Then go to frame 11 and cross the eyes and set keys again. Now go to the action editor and set the keys to linear interpolation and name the action something sensible, like eye cross. And remove the action from the armature. And now let's add an action constraint to the left eye from the eye target. We only want the eye target to scale on one axis. In this case, the x-axis probably makes sense, so lock the other two axes. Now let's configure the action constraint. This is exactly the same as with the finger, except the transform channel and action name are different. And now copy the action constraint to the other eye bone. Now if we scale the eye target, the eyes cross. Yay! The other thing that would be nice to improve is to make the eye target optionally stick to the head. In other words, we want a parent-child relationship between the eye target and the head that can be turned on and off at the animator's discretion. This is useful because sometimes, especially in more action-oriented animations, having to keep the eye target moving with the character can be a big pain, so the animator would probably want the target to move with the character's head in that case. But other times, we want the eye target to lock onto something external to the character, in which case having it move with the head would be a big pain. So it would be good to give the animator a choice between those two behaviors, so they can pick the one best suited to the particular animation they're working on. But how can we accomplish this? How can you make a parent-child relationship switchable? So we have two bones here, and let's try to create a switchable parent-child relationship between them. I'll start this by pointing out that one way to look at parent-child relationships is to think of them as the child copying the transforms of the parent, but also being able to move independently within that, right? If all of the transforms are exactly copied, then we get all of the squashing and shearing and scale and location just as we expect from a parent-child relationship. But then the child can also move independently within that. So part of this equation is pretty obvious. We can use a copy transforms constraint to make the bone copy the transforms of the parent. And since it's a constraint, we can use the influence slider to turn it on and off. But unfortunately, when the constraint is active, we can't move the child. So how do we make it movable? Well, the answer, perhaps a little bit amusingly,
Mechanism?
is parents.
Oh.
Remember that if we want to automate the motion of a bone, but we also want to be able to animate on top of that automation, we just give the bone a parent and put the automation on the parent, right? Well, that applies to this situation as well. Copying the transforms of the switchable parent bone is a form of automation. So all we have to do is give the child a real parent and then constrain that parent to the switchable parent bone. Let's give it a try. Remove the constraint from the child bone. Now add a new bone to be the intermediate parent. Parent the child to it. And now add the copy transforms constraint to it. Now when we move the switchable parent, the child goes with it. But we can still move the child as well. And if we don't want the child to follow the switchable parent, we just set the constraint's influence to 0. Whenever I need a switchable parent in a rig, this is how I do it. There is another way to do this, via something called a child of constraint, but I find this solution to be more reliable and flexible, and it really only takes a single additional bone, so it's not that complicated. Now we just need to apply this to our iRig. We need to add a bone to be the intermediate parent, and let's name it MCH iTarget parent. Make the iTarget the child of this new bone, and now constrain the new bone to the head. Of course, this makes the iTarget move away from its default position. To fix this, make the default position of the intermediate parent the same as the head. That way it doesn't move when it's suddenly constrained in pose mode. And now we have a switchable parent. Yay! However, this is going to be a bit of a pain for the animator. The constraint they need to change the influence on is a mechanism bone, which means it's normally going to be hidden. So we need another way for the animator to access the parent switching, preferably from directly on the iTarget control. Now, we could use a driver to drive the constraint influence using one of the unused transform channels of the iTarget, maybe one of the other scale axes. But that's not really intuitive at all. Instead, I'm going to introduce a new feature, custom properties.
Custom
Properties are pretty much exactly what they sound like. Bones and objects have a bunch of built-in properties like their transform channels, but Blender also allows us to add our own for whatever devious purpose we like. To do this, go to the iTarget's bone properties. Down at the bottom, there's a panel called Custom Properties. Open it up. This is where we can add any custom properties we want to this bone. Click the Add button. The default custom property is a number property named prop. To change this, click the Edit button. From here, we can change pretty much anything we want about the property. For starters, let's change the name of the property to something more descriptive, like follow head. Now, there are different kinds of content that a property can have. It can be a number, or it can be text. And even within numbers, it can be an integer, or a number that can have fractional components. The type of a property is determined by the default value you give it. So for example, if we type in some text, now the property is a text property. If, on the other hand, we enter a simple number, like 2, then the property is an integer. It can be any integer number, but if we try to enter a number with a fractional component, like 4.5, it ignores the fraction part. If we want to be able to have fractional numbers, then we need to put a decimal point in the default value, like 1.0, for example. In this case, we want a number that can be fractional, but we also want to limit the range of numbers it can be. If we edit the property again, we see that it has min and max fields. These fields define the smallest and largest number allowed in the property. In our case, we only want numbers between 0 and 1, since that's the range of the constraint's influence slider, so enter them into those fields. Lastly, if we want, we can even give the property a tooltip. Whatever we put in here will pop up when the mouse cursor hovers over our property. It can give a fuller description of what the property does. In this case, though, I think the property's name alone is descriptive enough, so let's confirm all of this. Click OK. Now the animator will be able to access any custom properties on the currently selected bone under Properties in the N panel. Now we just need to make a driver for the constraint influence. Let's grab the RNA path of our custom property since we're going to need it in a moment. Now go to the Copy Transforms constraint and add a driver to its influence slider. And now let's go configure the driver.
Okay, there we go. That's how that's going to work. So that's going to paste the property channel.
And paste the RNA path of our custom property into the path field. Now if we play around with headbone and our new custom property, we can see it working. Yay! The animator now has convenient access to the parent switch. And that's it. We're done with the eyes.
Wonderful.
Oh boy, now we get to talk about rigging arms. I'm gonna try and
Yay!
things in this video, so bear with me. The first thing is how to do IK-FK switching. We want Mr. Hot Dog to be able to swing his arms around, which is a lot easier to do with an FK rig, but we also want him to be able to hold on to things, which is a lot easier to do with an IK rig. So the obvious solution is to allow the animator
Learned from yesterday.
between FK behavior
I
and
had tissues near me.
there are a variety of ways that we can accomplish this. The first way depends on the fact that an IK bone chain is nothing more than an FK bone chain with an IK constraint on it. If we add an IK constraint to this bone chain, then we can control it with the IK target. But if we simply slide the influence of the IK constraint to 0, then we can use the arm like an FK rig. This is probably the simplest possible way to do an IK-FK switch, and for some rigs this may be enough. However, there are some problems with this. The biggest issue with doing things this way has to do with how inverse kinematics calculates the rotation of bones in an IK chain. Inverse kinematics figures out the rotation of bones based not just on where the IK target is, but also based on where the bone chain started. So, for example, right now if we switch IK on, the bones are put into this position. But if we change the FK position of the bones to bend the other way, then the IK solution bends the other way. And this problem only gets worse when we throw in pull targets. Basically, it makes things unpredictable for the animator, since the IK arm will behave differently depending on what they do with the FK arm. So if this is such a problem, why does Blender do things this way? Why not base it on the edit mode rest positions of the bones, for example? Well, the reason Blender does it this way is because it's actually a really good thing, and in other circumstances it allows us to do a lot of cool things that would otherwise be impossible, which I'll be getting into later in the video. It's only a problem in a few circumstances like this. And besides, we can work around it. So let's figure out how to do exactly that. The important thing here is that we don't want the IK bones to be directly rotated by the animator, right? So one way we can work around this is to make a duplicate bone chain that follows the IK target, and instead of turning the IK constraint on and off, we have copy rotation constraints on the FK bones that get turned on and off. If the IK chain is a hidden mechanism bone chain, then things will look identical to the animator, except they won't accidentally mess up the IK. So let's try that. Make a duplicate bone chain, offset it vertically a bit so we can see the difference between it and the original. We'll move it back later. Now delete the IK constraint from our FK chain. And let's constrain the FK chain to the rotation of the IK chain. Just add copy rotation constraints between the respective bones. Now if we move the IK target around, you can see the FK chain duplicating the IK chain's motion. Let's move the IK chain back down to match up with the original, and move them to a hidden armature layer. Now the FK chain is behaving exactly as if it were the IK chain. But if we turn off the copy rotation constraints, then it becomes an FK chain. But because the IK chain is not being affected by this at all, when we turn the copy rotation constraints back on, the chain goes back to the same position as before. It's consistent. And in a final rig, of course, both copy rotation constraints would be driven by a single custom property. So even though as riggers we have to manage these two separate constraints, the animator won't. The only thing we really need to do now is add bones for...
Wait, so now I'm thinking about how many rigs have I, like, seen, like, in my free time in the, how many hours have I been in Blender? 625.6 hours according to my Steam profile. And that's not even the messing around that I did before having my Blender be on Steam. Like, before, I'm not like a complete noob to Blender, but I only knew enough to know that I knew absolutely nothing, and it took 600 hours for me to get to that point, and now I'm just actually reading the manual and trying to figure out things from, like, first principles and whatever, because I was dreaming of trying to do this instead of actually doing it. So I imported rigs into Blender before, but I didn't know how to use pose mode or any idea on how to even move bones around so that they actually moved the rig. But now I'm thinking, like, okay, how many of those rigs that I tried to use had the absolute had just, like, multiple layers of mechanism bones that weren't even visible to me because I didn't know about the invisible armature layers. Like, oh boy, oh man. Ugh. The world is, in fact, even more complicated. Think about how complicated the world is and realize to yourself that it's even more complicated. So, I'm just, oh boy. Oh boy. Wonderful. Just wonderful. Okay, let's actually just continue.
When the animator is using the arm with IK, it makes sense for the IK target to serve as the hand control, so let's orient it a bit more sensibly for that purpose. However, it makes very little sense for the IK targets to be the hand control when the animator is using the arm with FK. Ideally, we'll want a separate control that is directly part of the FK chain. So let's duplicate the IK target, and make that duplicate part of the arm chain by parenting it to the FK arm chain with connected. And let's constrain its rotation to the IK target so it follows the IK hand when we're in IK mode. Try this out now. works. The character, in this case, would be parented to the FK chain, which does its own thing in FK mode, but copies the IK chain and controls when in IK mode. So this is a pretty nice solution. In fact, I think this is a perfectly fine solution for most rigs, and for Mr. Hot Dog I would be fine stopping here. But in the interest of teaching you a more complete solution, we're going to go a little bit further. The main problem with this solution actually has nothing to do with animators. The problem is that this actually makes things more difficult for us riggers. Let's say we wanted to add squash and stretch to the FK arm rig. Well, with this rig, we would have to be really careful about doing it in a way that wouldn't interfere with constraining it to the IK arm rig. And that's annoying. It would be a lot nicer if we could, as much as possible, completely separate the FK and IK rig so that we can think about the features and solutions for each rig separately. Remember that it's nice to rig in parts, so that we can focus on one problem at a time. We don't want things to get unnecessarily mixed up.
Okay.
Fortunately, this is an easy fix. All we have to do is introduce a third bone chain. The idea is that we have the FK rig on one side, and the IK rig on the other, and then we have a third bone chain in the middle that switches between copying the FK rig and the IK rig. The character will then follow this third bone chain. This way, we can think about the FK and IK rigs completely separately, and we can then deal with how to construct a bone chain that can copy both as a separate problem. This also has a side benefit for animators, which is that they never lose their FK controls. With our previous rig, when we switched to IK, the animator had no way of positioning the FK version of the arm. This isn't critically important, but it can...
So this is probably why there's so many armature layers that can be used. There's like 20 armature layers. How many rigs use like all of them? Oh no. Oh no. Oh no. I tasked myself to understand the Blender cover to cover. But oh boy. Oh boy. This isn't rocket science. It's not rocket science, okay? Yes, we use what are they called? So it's not inverse kinematics. It's what is it? It's the rotation thing that was a couple chapters ago.
Say hello to Mr.
No, it's not that one.
So the last thing I want to touch on before we get back to actual rigging is something called transform matrices. A transform matrix is a 4x4 grid of numbers that represents everything about... As I mentioned in the...
Right, quaternions. It's not rocket science, but we still use quaternions. Like for I don't think you I will say this over and over again. Fine. That's not what I... What happened to the website that I saw before? There was a specific website that explained it. What happened to it? MathWorks. Okay. OBS Studio disconnected. What? OBS Studio reconnection successful. Wait, hold up. Is friggin... Why did the internet disconnect and then reconnect? What happened? Is the live stream still going? Is the live stream still working? Did YouTube fuck up? Okay, that's fine. That's fine. Okay. We don't... The live stream is still going. Live stream is still going. Okay. That's perfectly fine. Things are working. But finally, after Google being like, oh, I'm not going to give you the website that you were looking for that you looked at literally like 2 days ago, it was the MathWorks website. Quaternions are vectors used for computing rotations in mechanics, aerospace, computer graphics, and visual processing, and other applications. So here's the thing. Blender is not rocket science. This is not rocket science. However, we do use rocket science concepts, apparently, especially when it comes to quaternions. Because that was a new word that I now know, and now am cursed to know, and I must give that knowledge. So, it's... The world is complicated, okay? The world is very complicated. However, it's not an insurmountable thing to understand. People have been doing this for years. People use Blender all the time. And I am going to be able to, you know, actually freaking do anything instead of being tired, depressed, and hopeless all my life. I need to learn how to use a tool. And the blender is a tool. I found my tool, and it's, all of these other people are just like, oh, pull yourself up by your bootstraps. That is an incorrect analogy. I believe that the better phrase to use is grab a shovel and dig your own trench. That is much better. And then you have to defend your foxhole. The important part is defending your foxhole. You can't abandon the front lines. You can't dig your trench and be like, okay, this is all done. Everything is gonna be fine now. No, you gotta man your station. You can't run away once the bombs start dropping. You gotta defend your position. So when things get complicated, you can't be scared or run away or give up. Giving up is losing. You can't give up. That doesn't get anybody anywhere in life. Retreating constantly doesn't get anybody anywhere. And I think I'm finally becoming myself in front of the camera now. Now I've done the live streaming on YouTube for long enough. It's like I can learn stuff. I can get better. I can go places, do things. I just need to work very hard at it. It's find your tool that you want to use. It can be literally any tool. But if you learn how to use that well, everything should fall into place. You don't... That's... I'm doing my best to find my meaning in life, okay? It's complicated, but just because something is complicated doesn't mean it can't be understood. It just means that you need to use it for a long time. Okay. But yes.
With how to construct a bone chain that can copy both as a separate problem. This also has a side benefit for animators, which is that they never lose their FK controls. With our previous rig, when we switched to IK, the animator had no way of positioning the FK version of the arm. This isn't critically important, but it can be useful when the animator wants to switch between IK and FK mid-animation. So let's put this into practice now. Remove all the constraints from the FK chain. And let's also move the IK hand to another armature layer so we don't get too confused. Now let's duplicate the FK bone chain and move it up a bit. This will be our intermediate chain. Also, move it to its own layer, and enable that layer so we can see it. Now constrain this rotation to the FK chain. And now let's name the constraints. Wait, what? Yes, that's right. We can give names to our constraints. For simple cases, this isn't really important. Heck, I'm not even naming the bones right now, since this is just our rigging playground. But in the final rig, we'll want things named for clarity. In this case,
okay, I want... It's 2 hours into the stream. I am out of tea. I'm going to quickly turn on the kettle a little bit. On. I'll turn up the music. I'm just gonna put water in the kettle. Put water in the kettle. Okay, water's in the kettle. The kettle is turned on. Let me actually give myself a timer. Okay. How long does it take for a kettle to boil? I don't know. I'll just put a 5-minute timer and see if it's hot. Okay. I can be myself. This doesn't... Live streaming doesn't have to be a performance. I can literally just be myself. This is crazy. Oh. Okay.
Which constraints are for FK and which are for IK. So name all of these constraints FK.
I don't think I've been paying attention for the past 10 minutes.
And unhide the IK layers.
Oh boy.
Chain to the IK bones. And name those constraints IK.
I can just watch all of
Now
this.
unhide all of the layers and let's play with this. Right now it's following the IK chain. That's because we added the constraints for the IK chain after the ones for the FK chain. So they're later in the stack, and therefore overwriting the constraints to the FK chain. But if we slide the IK constraints influence to 0, now it follows the FK chain. So in the final rig, all we'll need to do is drive the IK copy rotation influences with a custom property, and bam! Instant IK FK.
That's
of course,
not the 5-minute alarm. That was the 1:30 alarm, which I also have.
I just have it offset so it's not so confusing when we're building it. So are we done now with the arm rig? Well,
No.
No. We now know how to switch between the IK and FK rigs, but we still need to design each of them. Yeah, this is a long video. Sorry. So let's start with the FK rig. You might think there's really nothing more to an FK rig than just having a simple FK bone chain. And you would almost be right about that. But there's one teensy-weensy feature that can make things a lot nicer for animators. And that's the ability for the arm to not follow the body's rotation. Let's say we have a character jumping up and down, waving at someone. The body would be rotating back and forth as part of the jumping, but the arm would be doing its own independent rotations as part of the waving motion. The problem is that if the arm is simply the child of the body, then it's going to be following the body's rotation, which the animator will then need to counter-animate against. When I was animating on Big Buck Bunny, this was actually a huge problem with the rigs. And unfortunately, I had no one to blame except for myself, since I did the rigging for it. I cannot tell you how much counter-animation I did on the character's arms. It was a lot. That's not to say that limbs aren't affected by body's rotation, but it's a loose, indirect relationship. If I swing my body around, my arms have a delayed flopping reaction, and having the arms follow the body's rotation directly would actually hinder, not help, an animator achieve that effect. In fact, having the arms follow the body directly is so unhelpful that I have often been tempted to just remove that behavior from my rigs entirely. However, there are a few circumstances where it can be helpful, like with, robots, I guess. Or a character doing the robot. So we're going to make it something that the animator can turn on and off with a slider. The process for this is actually really simple. It's almost identical to the switchable parent, actually. If you think about it, all we really need to do is make a switchable parent, except we want the bone chain's location to stick to the parent even when the switch is off. So all we need to figure out is how to make the bone chain's location stick, because we have the switchable parent figured out already. So we have a body bone and an arm chain here. If we want the arm chain's location to stick with the body bone, we can do it with a simple copy location constraint. So constrain the base bone of the arm to the location of the body bone. Well, although this works in a sense, this obviously isn't quite what we want. We want the bone chain to stay in the shoulder socket, not the hips. But this is pretty easy to do. Just add another bone where we want the arm bone to stick, and make it the child of the body.
Oh, I just have my funny bone.
Since this bone is the child of the body, it goes with the body. And now we just have to constrain the arm to this bone. And now if we move the body around, the arm sticks. But it doesn't follow the rotation. This is exactly what we wanted. Excellent. I like to call this a socket rig.
Okay, hold on. That's the 5-minute timer. That's the 5-minute timer. I'm not gonna change the volume on the music. Hold on. Okay, tea is poured, it's hot, and it's steeping, so I'm gonna hit another 5-minute timer. Then I'll have more tea, and I think I might be going into an upswing of a manic episode, actually. I need to be mindful of that. I need to be mindful of my behavior right now. Ooh. Will I have a depression crash later? That's the bad part. I don't like that. So here's the thing. I get excited, and then after I get excited, there's a crash, and I need to both temper my excitement and pull myself up when it's a depression, like, downswing. I have to be constantly aware of my brain and what I'm feeling at any given moment, and it is tiring. However, I don't know how else to describe it. Wave over wave, sea over bound. And there's happy men as sea would allow.
Socket, and the arm stays in that socket. Now to make it switchable, we just have to layer on a switchable parent. There are actually multiple ways to do this, but I like to try and keep all of the constraints on a single bone when reasonably possible. So for the arm's real parent, I'm simply going to make a duplicate of the socket bone and unparent it from the body, and make the arm the child, of course. Now remove the constraint from the arm. The arm is no...
I'm too in my head right now.
Now just add the copy location constraint to the parent instead. And as long as the parent and the arm are in exactly the same location, this behaves the same as what we had before. We also have the bones needed to do the parent switch. Just add a copy transform constraint between the socket bone and the parent bone. Now the arm behaves as a child of the body. But but we can turn that off by just turning the copy transforms constraint off. I like to call this rig a socket switch. And that's pretty much it for the FK arm. We just need to choose our rotation modes and access locks. The upper arm rotates on all 3 axes, so it makes sense to leave that as a quaternion. Otherwise, you can run into major gimbal lock issues, especially in combination with the socket switch. However, we don't want the animator to accidentally pull it out of its socket, so let's lock the location axes. The forearm only rotates on one axis, so Euler rotation with only one free axis makes a lot of sense here. And we're just going to leave the hand alone. It's not horrible to set the hand to Euler as long as you choose the rotation order well. After all, it mostly just rotates on 2 axes. Mostly. But I like to leave it as a quaternion, since it will be more consistent with the IK hand. The IK hand will be quaternion since it's floating in space, and needs to rotate on all 3 axes to orient itself in various ways. So that's it for the FK arm. Hurrah! For the IK arm, we also don't have a whole lot to do. In fact, we're going to do nearly exactly what we did for the IK leg rig on Mr. Squeegee Feet. So I'm not going to cover that again, just go back and watch that video. But I do want to expose you to 3 things. The first is a clever little trick I figured out not too long ago. The second is an alternative way to control elbow and knee direction. And the third is showing the weird way that IK interacts with the constraint stack and how to work around it. So first, the trick. Remember way back in the Squeegee Feet tutorial, I told you to keep the knee bent in the default position? Well, now you know why. It's because the IK solver uses the initial position to determine how to make it reach the IK target. In particular, the knee will tend to bend in the direction that is already bent. But now that we know that the IK solver uses the current pose of the bones, not their edit mode positions, we can use a trick so we don't have to have the edit mode bones slightly bent. This can be really useful. Sometimes the models we want to rig have straight arms or straight legs, which means...
Okay, that's another 5-minute timer. Putting sugar in my tea. Super hot. Super hot. I'm just gonna leave that for a minute. How long do we leave tea to cool? I don't know. I'll just put, like, what? The 10 minutes on a timer, I guess. Leave the lid open, I guess. I have no idea how things work. I know just enough to know that I know nothing. And that is a scary place in your when you have a brain like mine, because it's, you get depressed because you don't know anything, but you then get excited because once you do know just a little bit about something, is there's a Dunning-Kruger effect. You think you know everything, and then you gotta constantly be like, no, come back down. No, I know nothing. Friggin', it's ridiculous. My brain, I hate it and I love it, and it's complicated and it's got trillions of neural connections, and it's just a meat computer. It's a meat computer inside of a skull, inside of a body that is both always too excited or too depressed. Is just like, ah. today is different. I'm doing my best. The stream title, of course, is Who Am I? I am the Jaded Company, I guess. I am tired and pretentiously calloused, and I've been overstimulated by a lot of things for my entire life. The internet is quite an overstimulating place, and it's just like there's so much places in which there's information, but there's so much information that also doesn't feel like it tells you anything. I hope other people have the same experience, because I don't want to be alone in this. I needed to sneeze. I muted the microphone this time, that was good. I'm getting better. I'm getting better at streaming. It's crazy. I'm getting better. Somehow. I actually used to stream on Twitch quite frequently when I was younger, to put it mildly. But it's just like I both also didn't know who I was. Yeah. That's really the crazy part. You sometimes don't know who you are, and then when you figure out kind of a little bit of who you are, or what your life's purpose could be. Oh, I almost spilled my tea. I should probably put that further away from where my elbow decides to bonk it. But like once you figure out a tiny modicum of who you are and what you want to do, it's like, okay, this is maybe just maybe you can make something with it. And it for me, I don't know what I'm going to be doing, but I do know that I need to know how to use the tools that I want to use. And the tool that I want to use is Blender. And I know absolutely nothing, but I know it's capable of so much. It's capable of so much. Same with Linux. I'm on Linux Mint. I think it's great. I think Linux Mint is awesome, actually. The problem I used Arch Linux for a little bit. That was frustrating and also fun. And as when there was a problem, and then I figured out how to fix the problem, it was just like, oh my gosh, I am big brain. I am the greatest. I am awesome. But then it's just like, no, I have a friend of mine that spent arguably more time on it, and they and I feel left behind. I feel left behind on so many things. Because I didn't apply myself to any one thing. Being a generalist is spreading yourself out so far and so thin, but a broad understanding in anything, a broad understanding spanning across like many subjects is the key to being like socially flexible, I guess, because you're able to relate to any one person like immediately because you have some sort of common ground, but then it's like you're not able to definitively access a specific thing that you feel is your life purpose. Like, it took me a long while to figure out what I actually wanted to do with my life, and I'm only finally settling on wanting to use Blender because it's like it's Blender and content creation. There were several times in which I tried to do like a YouTube or a Twitch or anything, but then it's just like I worked on it, and I tried to be regular with it. I tried doing it over and over and over and over and over again, and then, but I was also like not locked into a specific thing. I was just doing random things all over the place. So gaming is it's fine. However, it's not video games. They can be, they're fun. Not, I won't discount the fact that they're fun. However, like, I only get like so far into a game before I start feeling like, okay, but is this like helping me at all? Am I learning anything that can be like used in my real life? And the thing is that like I live streamed, I live streamed, I made videos and posted them onto YouTube. But then it was just I was trying to chase views and trying to create a community. But the thing is just playing a video game isn't something that I am actually passionate about. Playing a video game was just the means to an end, and the end was just like, okay, maybe people will like me and stuff. However, that's the wrong way to go about it. People will only like you if you're doing something that you actually like doing. And you can actually be yourself, which is something. I'm not talking to anybody right now. The stream is empty, there's 0 viewers, but that doesn't mean that I can't be myself. I gotta be myself regardless of who's watching. That's even if nobody's watching. Who you are when nobody is watching is is trying to be yourself, but you also need to try to be yourself even when people are watching. And I guess I'm accidentally giving myself talk therapy because okay. I am very in my head. How much of this playlist do we have? How much of this playlist do we have? We still have a lot of this playlist. That's perfectly fine. I don't understand everything that is happening. But by the end of it, I am also going to continue reading the manual. And I love reading manuals. Manuals are great because they actually give you information in a way that's just like, yeah, manuals are good with prior knowledge, but it's also doing its best to try and give you the first-hand knowledge. And I guess that's also why they put this Blender tutorial in the C also. Related sections. Yeah, it's just like they had humane rigging as a link in the manual. How many manuals do that? This is great. Okay, I'm just gonna hit continue, and I'm going to do my best to actually absorb passively this knowledge.
The bones need to be straight too. We have here a totally straight bone chain. If we turn this into an IK chain, it can't decide which way to bend, and it kind of freaks out. But even though it's not bent in edit mode, we can just manually bend it in pose mode. And now it works just fine. Cool, right? However, we don't want to rely on this pose adjustment staying put. Even locking the rotation axes isn't enough to make me comfortable with this, because the user can
He's still too hot.
Numbers. They're really only pseudo-locked. But remember earlier in the 3D ball chapter, when we wanted to lock the rotation mode of a control? We just added a driver to it with a simple number as the
What is Steve doing?
We're going to do the same thing here. Right-click on any of the rotation channels and select Add Drivers, plural. If we go to the drivers interface now, we can see that Blender automatically filled in the driver expression with the current value of the channel. Blender will automatically do this for numerical fields like the transform channel, so we don't actually have to configure the drivers at all. That makes adding drivers a convenient way to lock almost anything in a rig. And that's the trick. Just bend the forearm bone in pose mode, and add drivers to the rotation channel. Your arms can then be as straight as you want in edit mode. I like to call this IK hinting, because we're giving the IK solver a hint about how we want it to position the arm. The next thing I want to show you is an alternative way to control the knee and elbow direction of an IK chain. I've already set up a basic IK arm, with the elbow locked to only rotate on a single axis. The way we did this on the leg rig was to add a pull target that the knee points at. But if we want to, we can instead take advantage of the fact that inverse kinematics solves from the posed position of a chain. If we give the chain a parent, then we can rotate the parent bone to determine the elbow direction. This works because under the hood, if we turn IK off, the arm chain is rotating along with the parent. So when the IK is active, it's calculating things based on that starting position. This method can work pretty much just as well as the pull target method, and the animator can more or less think of the elbow as pointing in the same direction as the parent bone. The only thing to be wary of is that the twist of the parent bone needs to not stray too absurdly far from the IK target, because then it starts doing weird things. although it is still pretty forgiving. But it can sometimes be a bit more for the animator to have to think about, and it may not always be obvious to the animator why it behaves weirdly. But still, for some situations, I think this method of controlling elbow and knee direction can actually be better than pull targets. It just depends on the situation. For Mr. Hot Dog, we're still going to stick with pull targets, but I just wanted to show you this because it can be useful. So the last thing that I want to talk about is how inverse kinematics fits into the constraint stack. The tricky thing about inverse kinematics is that, unlike most other constraints, it affects multiple bones. And because of that, it always gets applied after all of the other constraints on those bones. To understand why, let's take a look at yet another silly little drawing. We have 3 bones here, each with their own constraint stack. The last bone has the IK constraint on it, but that constraint actually affects both of the other bones. So if the IK constraint is, say, in the middle of the last bone's constraint stack, when should it be applied to the other bones? I suppose it could just be applied as if it were in the same position on the other bones, but if we did that, then even if we put it last in our last bone's stack, it would still only be applied partway through the first bone's stack, which would be confusing. But it gets even more complex than that. You see, multiple IK constraints can actually work together on a branching chain in Blender. If there's an IK constraint on this bone that affects bones all the way back to here, and there's another IK constraint on this bone that also affects bones all the way back to here, then the 2 IK constraints need to cooperate on the shared section of bones. And that means they both need to be executed at the same time. But they're 2 separate constraints, and could be in completely different places in their bones' respective constraint stacks. So in order to avoid all of this confusion, the IK constraint is considered unique, and instead of getting evaluated where it's placed in the stack, it always just gets evaluated last. That pretty much makes sense. Except, what if we want additional constraints to be applied after the IK constraint? Fortunately, there's a cool trick you can use to accomplish this. I have a simple IK chain here, and the main observation we need in order to get around this limitation is that the IK constraint is only executed last on the bones in the IK chain, not on any other bones. So if we make a duplicate of this chain, and we constrain the duplicate chain to the IK chain via copy transform constraints, then the second bone chain now does exactly what the IK chain
Reconnecting?
copy transforms.
What was OBS? Why? Why OBS? Hold on. Why? OBS, why? What is the problem with the... OBS? Is everything okay? Stream still going? Okay. Fine. Okay. That's fine. That's fine. Okay. We got... I don't understand why OBS is disconnecting and reconnecting. It never used to do that. It never used to do that. Okay. The tea is cooled down enough. The YouTube short that I posted at the beginning of before the stream started was actually doing pretty well. It's that's great. That's great. I love it when I can share myself and people seem to enjoy it. Because I would love to be seen, not like as like a viewing scene or like getting views or people watching me, but it more like seen like on an emotional level. Like my brain, I am in fact a living being, and that may be a rare thing to find on the internet nowadays, because like you can't tell whether or not somebody is AI, or like if it's like something is actually like real. But like it's crazy, and I just want to be seen and to do something that I can be proud of, like better than what, friggin' Gemini or GPT like wants to do something. And it's just like these AI data centers, so much money to do a fraction of what like a good best friend could do. Like if a best friend, if you have a best friend that you're able to like talk to, like they will always have you can have a much better and deeper conversation with that friend than you would with any like chatbot. That's just my belief internally, because a best friend doesn't necessarily tell you things that you want to hear. They tell you things that they feel like you need to hear. Because they care. It's all about somebody caring about you. And a machine doesn't have the ability to care about a person's well-being. It only cares about what it was trained to be, which is a product of use. Like, it exists and was programmed to be used as much as possible. Its only goal as a tool is for somebody to keep using that tool. It's an addiction algorithm. It's not even a shovel. Like a blender metaphorically is a shovel. You can do work with a shovel. But these AI algorithms are just like, hey, I'm going to be a shitty shovel, but I am going to make it so that I constantly change the size and shape and what the shovel does with every single scoop to attempt to get you to use the shovel again. Like, it's consistency. Consistency is impossible with with AI. It's not a consistent tool. It constantly changes and evolves, and it's not a static form that you can rely upon. It's a... I don't know how else to describe it. It hallucinates, it gives you incorrect information, it gives you out-of-date information. It's useless, especially when it comes to trying to give me information that I don't know yet. You have to already know something in order for AI to tell you something, because it's only like an extension of what you've already told it. Or what it already has been told. It can't create new information. It can only access pre-existing information, and the problem is the things that I want to do aren't necessarily pre-existing. I'm flesh and blood. I can't. I want to do things that haven't been done before. AI can only do things that have been done before. I don't want to do things that have been done before. So AI can't help me. I don't want AI to help me. It's, I'm now 3 hours in. So, let's just continue. That's the wrong pause and play.
Is basically just a way to extend the first chain's constraint stack. Back to silly drawings again. Essentially what we're doing is applying all of the constraints we want to happen before the IK constraint. Then we have the IK constraint. Then we transfer everything to another bone chain. And then we apply all the constraints we want to happen after the IK constraint. Then you can attach the character mesh to that second bone chain, or it can be part of some larger mechanism, or whatever. Anyway, I haven't actually used this in a rig quite this directly yet, at least not that I can remember, but it's worth being aware of. You can get around the fact that IK constraints are always executed on a bone last. So there we go. That's everything that I wanted to talk about in this video. Whew. So we figured out how to rig all the parts. Now we just need to put everything together. But wait, except for the eyes, this character is one single mesh. And things like the body mesh need to be affected by more than one bone. So how do we do that? Well, that actually gets us into a huge topic that is, unfortunately, beyond the scope of this DVD. And that topic is deformations. However, I will show you the barest of bare basics. Blender has a way to dynamically affect meshes, which is called the modifier system. We can access the modifiers for any given object by selecting that object and going to the modifier properties. It looks a lot like the constraint stack, and, well, that's because it is a lot like it. In fact, this is called the modifier stack, and it behaves pretty much identically to the constraint stack. The only difference is that the modifier stack affects meshes and other internal object data, whereas the constraint stack only affects transform matrices. Other than that, they both behave the same way, taking input at the top, modifying that input as it goes down through the stack, and spitting the result out the bottom. I already have two modifiers on this character. We can see what they do by turning them off and on. The first modifier is called a mirror modifier, and it mirrors the mesh across an axis. In this case, I used it so that I could be lazy and only model one half of the character.
Oh,
The next modifier
okay.
is the Vision Surface modifier. It subdivides the mesh, smoothing it as it goes. This way, I only have to model a low-resolution character. So this is all well and good, but what does this have to do with multiple bones affecting our character mesh? Well, it has everything to do with it. We use a modifier to make an armature modify the locations of mesh vertices. That modifier is called the armature modifier, and it lets you assign certain vertices in the mesh to follow certain bones in an armature. Now, the important thing to realize is that not every bone in the rig should have vertices directly following it. For example, in our finger rig, we want the vertices to bend with the finger digit bones, not scale with the finger control. So whenever I start out rigging a character like this, I always start by laying out the bones that I want to directly affect the mesh. I call these bones deformation bones because they deform the mesh. So let's get started with that. Let's add an armature to the scene, and make it wire X-ray and turn bone axis display on. And the first thing I do before placing deformation bones is to turn on wire display on the mesh. Go to the object properties, and turn on wire display. Note that this is different than wire display from the menu. This overlays wireframe on top of the solid mesh. It also looks kind of incomplete. Not all of the edges are showing. To fix that, go to Display in the end panel, and with the mesh selected, toggle on All Edges. Well, that didn't do much, did it? That's because of a weird behavior in Blender. To make that option actually take effect, you have to enter and exit edit mode on the mesh. Don't ask me why. I think it's pretty darn silly. Okay.
Okay.
Here we go. The reason this is important is because the quality of our deformations partly depend on the placement of our bones as compared to the vertices of the mesh. So now we can start adding our deformation bones. Let's start with the body. We're going to use 3 bones, evenly spaced. So move the tip of the default bone up to be the first third, lining it up with an edge loop. Now extrude the second 2 bones from that. And let's align the bones so that the x-axis rotates forward. And of course, let's name them. Now let's add the bones for the arms. Don't forget x-axis mirror to speed things up. And align and name them. Make the arms the children of the topmost body bone. Now for the hands and fingers. Make sure that the fingers are the children of the hand, and align and name them. Note that I'm aligning the hands and fingers differently than the arm, because the most common axis of rotation is different for them.
Oofaroonie. This is a lot of renaming. Well, I mean, 50% of the bones in the human body are like just in the hands, aren't they?
And verify that we got the naming right for mirroring. And finally, let's create the eye bones. Remember, we want them to be at the center of the eye, pointing in the same direction.
Yeah, the hands have 27 bones. According to Wikipedia. Gotta love Wikipedia. I love Wikipedia. Wikipedia, stay winning.
And make sure they're the children of the top body bone. There we go. That's all of our deformation bones. Hurrah! But before we start building our rig designs on top of these, I think it's a good idea to make sure that the deformations will work with this layout. Because if, say, you go and build all of our complex rigging on top of this, only to discover later that, say, the body needs more bones for good deformations, or that the finger joint should be placed slightly differently, it would be much more painful to adjust. The first thing to do is add the armature modifier. The easiest way to do this is actually through a shortcut in the parenting menu. Select the mesh, and then the armature, and hit Ctrl-P to parent. There's an item labeled Armature Deform, with several sub-items underneath it. In addition to parenting the mesh to the armature object, these menu items also automatically create an armature modifier on our mesh. The sub-items also do some additional things. I'll only mention two. The first is the Empty Groups item. This will create vertex groups for each of the bones in the armature, but it won't set them up for deformations. I'll explain what vertex groups are in a moment. The second is the Automatic Weights item. This adds vertex groups for each bone, and it also tries to automatically set them up for deformations. In our case, we don't want the computer to do any of that automatic weighting stuff, so select Empty Groups. You'll notice that the wireframe of the mesh suddenly got denser. That's because the armature modifier that was just added comes after the subdivision surface. Blender tries to simplify the mesh view of the subdivision surface modifier when it can, but it can't do that when another modifier comes after it. In any case, we want the armature modifier to come before the subdivision modifier anyway, so that the smoothing gets applied after the deformations, not before. We also want the armature modifier after the mirror modifier, so that it will deform the two sides separately, instead of both sides always doing exactly the same thing in mirror. So move the armature modifier up one item in the stack. And finally, uncheck bone envelopes so that the armature only uses vertex groups for the deformations, and check on volume preservation, which will make our deformations in this case a little bit nicer. Now we need to set up the vertex groups. What are vertex groups? If we go to the mesh properties, we see that there is a vertex groups panel. This is the list of vertex groups on the mesh. You'll notice that these groups have the same names as the bones in our armature. This is not a coincidence. By default, a mesh's vertex group list is empty. But when we parented the mesh to our armature with the empty groups item, it automatically created a vertex group in the mesh for every bone in the armature. I won't go into the details of vertex groups since they're used all over the place in Blender, but in our case they will serve to let us attach vertices to the bones in our armature. Bend the middle body bone in pose mode. Right now, none of the mesh is following the bones of the armature, but we can change that. Go back into edit mode in the mesh, select this edge loop with Alt-right click. Now, to make this edge loop follow the middle body bone, we need to assign the vertices to the vertex group with the same name. So let's find the vertex group called body.02 and select it. And now let's click the Assign button. And now exit edit mode. Whoa! Those vertices are now following the middle body bone. If we go back into edit mode, however, the vertices aren't moved anymore. To see the effects of the modifier while we're in edit mode, we need to toggle on a couple of options on the armature modifier. This one, and then this one that appears afterwards. Awesome. Now, the real power of the armature modifier and vertex groups is that a vertex can belong to more than one group. Let's try assigning these vertices to the top body bone, body.03, as well. And now rotate the top bone in pose mode. It now affects the vertices as well, but notice that the middle bone still affects them too. What the armature modifier does is when a vertex belongs to more than one group, it positions it based on the average of where it would be if it belonged to each. But it's not just a straight average, it's based on weights. If we go back into edit mode on the mesh, we can see a panel in the end panel called vertex groups. This shows us the vertex groups that the currently selected vertex belongs to. It also shows us the weight that the vertex has for each group. If we tweak the weights, we can change how much each bone affects the vertex. Larger values mean more influence, and lower values mean less influence. And we can copy the displayed weights to all of the currently selected vertices by clicking Copy. So this is how we're going to attach the mesh to the armature. Let's start with the body. To keep us from accidentally selecting vertices from the arms, select both arms using the L key, which selects contiguous mesh pieces, and press H to hide them. Don't worry, we can get them back. They're only hidden, not deleted. Now let's select all of the vertices that we want to only be affected by the top body bone. You'll probably want to go into wireframe mode by hitting Z, and select them using box select by hitting B and left-click dragging. Now assign them to the top body bone vertex group. Hey, look at that! It just jumps right to it. Cool. Now let's do the same for the bottom of the body. In this case, the vertices didn't move because the bone hasn't moved from its default position. Now we need to deal with the middle of the body. This is the tricky part. We need to balance all three of the body vertex groups together so that there is a nice, smooth blend over it. Good weighting is unfortunately beyond the scope of this DVD, but I'll just go ahead and do it, and you can copy if you wish, or practice trying to balance it yourself. There is a certain art to it, so it takes practice anyway. We can unhide the arm vertices with Alt-H. Weighting the rest of the mesh is a similar process. So now I'm going to do the rest of the weighting. Just keep in mind that because we have a mirror modifier, we're really only weighting the left side of the body. The mirror modifier automatically mirrors the weights to the other side. notice that I am often doing the weighting in a posed position so that I can directly see how the weights are affecting the deformations.
Okay. Continuous mesh select. Hold on, I need to... Where's the Blender manual? Where did it go? Where's the Blender manual? Oh, hold on. Okay, there it is. Went onto a hidden screen. Sorry. I'm getting back to the video. There we go. I need to find where continuous mesh select is. Selected link selects all geometry that is connected directly or indirectly to the current selection. This is often useful when a mesh has disconnected but overlapping parts. Or isolating them any other way would be tedious. So... Control L.
And lastly, parent the eyeballs to the
Okay.
thumbs.
That's a Blender manual.
Whew. Now our character is all set up for deformations. It's taken us a while to get here, but it's finally time to put the whole rig together. Let's start by naming the armature, which we haven't done yet. Name it Rig, like always. And let's also get things rolling by adding a root bone. That way we can parent things to it as we go along. Remember to position and align it so that it matches with the world axes. And, of course, name it root. And right away, let's parent the bottom body bone to the root bone. The thing that makes a root bone work is that everything in the rig is either directly or indirectly its child. That way everything ultimately exists inside its space and moves with it. So as we go along rigging, we need to make sure that anything that isn't already the child of something else is the child of the root bone. You can verify that the root bone is working properly at any time by just selecting it in pose mode and moving it around. If everything moves with it properly, you're golden. But if not, that means you missed a parent-child relationship somewhere. Either that, or you were silly enough to think that turning off inherit rotation was a good idea. These ideas can be nice shortcuts in a quick throwaway rig, but you should avoid them in full character rigs. They make setting up a proper root bone nearly impossible. And besides, there are other ways to accomplish the same effects. For example, the socket rig we first made for the FK arm does exactly the same thing as toggling inherit rotation off, except it doesn't interfere with creating a root bone. Now let's add the controls for the body. It's just 2 additional bones. I'll make them by duplicating the top and bottom bones. And make sure to parent them to the root bone, since they're not going to have any other parents. And let's name them. And let's add the copy transform constraints. In this case, there's only one middle bone, so adjusting the influence of its constraints is pretty simple. And now resize and position the controls appropriately. And constrain the top body control to the location of the bottom body control. Let's test and make sure everything is working so far. Awesome. Now let's do the arms. Remember that we need to make the FK controls and IK controls separately, and then we have the bones that actually control the mesh switch between them. So let's make 2 duplicates of the arm and hand bones, one for the FK controls and one for the IK controls. Offset them vertically above and below the bones that deform the arm. We'll move them back when we're done. Now let's name everything. We'll make the top bones the FK arm, and the bottom bones the IK arm. We're just going to use FK and IK to distinguish the 2 arms.
Lots of naming. Lots of naming. Boy.
And remember that the IK arm bones are never directly touched.
So my spine. My spine be poppin'. My spine be poppin'.
And now let's set up the FK rig. Create a socket bone and a parent bone for the arm. Now name the bones. Remember, these are both mechanism bones.
I feel like I'm gonna need to rewatch this series again.
And don't forget to do add the copy location constraints. Now if we rotate the upper body control, we can see our FK controls not following the rotation, just as we expected. But what about rotating the root bone? Oops! The arms don't follow the root either, which is not what we want. Everything should follow the root. The reason this happened is because we forgot to make the arm parent the child of the root bone. So let's fix that. Make the arm parent the child of the root bone. Now the arms follow the root bone. Woohoo! But they still behave properly when rotating the body. Awesome. Now let's add the copy transform constraints, which will allow us to make this a toggleable behavior. Now if we rotate the upper body bone, aha, it follows! Wonderful. Now we need to set up the custom property to control this switch. Unfortunately, there isn't an obvious best choice for where to put the custom property. It's partly a matter of taste and partly a matter of use case. But for Mr. Hot Dog, we're just going to put it on the upper arm. We're going to call it Isolate Rotation. And make sure it has a min and max value of 0 and 1. Now let's copy its RNA path and add and set up the driver on the copy transforms constraint. Let's test this out now. Rotate the upper body control and slide isolate rotation on and off. Well, it seems to work well, except that the slider seems to do the opposite of what it says. When it's turned all the way off, the arm's rotation is isolated from the body, and when it's all the way on, the arm's rotation follows the body. That's not what the name of the slider indicates. That's the opposite. You would expect the arm to be isolated when the slider is on. This is where I get to introduce a new aspect of drivers. You see, it's no coincidence that you configure the drivers in the F-curves editor. Now, we could just adjust this driver by using scripted expressions and entering 1.0 minus var, and that would flip the behavior of the slider just fine. But that would be no fun. Then I'd have no excuse to expose you to the third part of drivers. Remember, in the drivers panel, there are two parts, the variables and what is done with those variables. Well, there is also a third part, which is the F-curves editor. The value produced by the what is done with variables part is further processed by an F-curve. If there is no F-curve associated with the driver, it will just use the value directly. But if there is an F-curve, it will find the horizontal position that corresponds with the value, and then use the vertical value there as the result. So, for example, if the value out of here is 0.5, then the driver finds 0.5 on the horizontal axis, and finds the vertical position of the F-curve at that point, and uses that value as the final driven value. So you've probably noticed two things by now. First, there's already an F-curve here, and secondly, we ended up at 0.5 again. The reason there's already an F-curve is because Blender automatically adds an F-curve generator to drivers, and that generator maps every number to itself. This generator is one of many so-called F-curve modifiers, and they are quite powerful tools. They allow you to procedurally generate and alter F-curves, and they do so in the same stack-based way that constraints and modifiers do for matrices and geometry. I definitely recommend playing around with these F-curve modifiers. In fact, we could accomplish what we want by tweaking the values of just this generator here. However, I think it will be easier for us to simply create an F-curve manually. And to do that, we need to delete the generator. So click X to remove it. To reverse the effects of our slider, we want to map 1 to 0 and 0 to 1, right? Whenever the the slider is at 1, we want the constraint influence to be 0, and vice versa. So for the first point on our f-curve, let's find the horizontal 0, and place a point at vertical 1. This will map 0 to 1. To add the point, hold down Control and left click. For the second point, we want to find horizontal 1, and place a point at vertical 0. This will map 1 to 0. If we test this out now, yay, it works! However, we're not quite done yet. Right now, our f-curve is curved. Also, since we placed the points by hand, they are almost certainly not at exactly the values we want. To address the first problem, we simply select all the points, hit T, and select linear. Now the f-curve forms a nice straight line. To make sure the values are exactly how we want, we can select one of them and go to the Active Keyframe panel. Here we have direct access to the selected point's coordinates. And as we suspected, they are not exactly what we wanted. So let's enter the values we did want. And let's do the same for the other points. Awesome! Now our driver is perfect! This ability to create f-curves to alter drivers' behavior is extremely powerful. It's kind of overkill for this situation actually, but there are many cases where it can be invaluable to create complex driver curves. Finally, let's set up the rotation mode and axis locks for the bones. I'll do all of this same stuff to the arm on the other side now, but off-screen. It's exactly the same process, just keep in mind that we want separate control of the rotation isolation for each arm, so make sure to create and use a custom property on the other arm as well. Now it's time to build the IK arm rig. The process for this is identical to the process for Mr. Squeegee Feet's leg rig, so go back and watch that for detailed instructions. I'll just breeze through it here, only highlighting things you should take special notice of. Before we do anything else, we want to unparent the IK hand, since it's going to be the IK target. However, we do want the IK hand to move with the root bone, just like everything else, so make it the child of the root bone. And now let's create the pole target, naming and positioning it appropriately. We want this to be the child of the uppermost body bone. Not the control for the upper body, but the actual bone. That way, the pole target will follow the body in an appropriate way. And since this arm is perfectly straight, we'll want to do IK hinting on the elbow so that it doesn't freak out. Bend the arm slightly and add drivers to its rotation channels. Now let's do all the IK setup, just like on the leg rig. Ta-da! That's it for the IK. Now I'm going to do the same thing for the arm on the other side. I'll be back in a jiffy. Now we just need to constrain the intermediate arm bones to the FK and IK arms. First, add the constraints for the FK. Then the IK. And name the constraints. And now we need to make...
I'm sorry, I'm not really adding I'm sorry, I'm not...
Another case of there not really
Okay.
being an obvious best place for it to be.
There. Okay. I'm sorry I'm not really adding much commentary right now. I think this is the crash I mentioned earlier. So what can I do to alleviate this? Um Still going through this video. But here's the thing, is there anything that I can do here given what I've learned? Is there anything that I have learned that I can apply? I've been just passively watching. I don't think that's good. Control P. Parent to the bone. No. Armature deform. Constraints. Delta. Shape keys. Physics. Modifiers armature. Vertex group. No results found. Armature. Pose node. No. delta, bones, constraints, object. Bone, deform, yeah. Um, I don't think that was the right way to go. Um, Parent with empty groups? Um, Modifiers? Head. Okay. Now, in pose mode, no. That doesn't do anything. Preserve volume. Modifier and remove. Um, one. Bone 03. What's bone 03? Um, the location in edit mode got messed up. Oh no. Oh no, I messed up. Okay. Uh, 3 o'clock alarm. Armature. Pelvis, bone 0. Collections, bones. Body. Bone 03. Bone 03. Bone 01. So I ended up having weird bones. So that's where that extra bone came from when I first made it. So here's the thing. I need to control parent with empty groups. Okay. And I take the head I'm gonna close the armature. Now I need the armature because I need to select the cube. And I need to bring properties. Go to modifiers. Vertex group to head. No, that didn't do anything. Bone constraints, bone. Data. Need object mode, select, data, vertex groups, head. Shape key at current frame. Oh, I'm gonna keep that at 0.3. Vertex group. Head. Object mode. Pose mode. UI. Nope, that didn't do anything. Object mode, select. Preserve volume. No. Bone 01 and Bone 03 still exist. Sign. Was that the thing? What was that the Now. Modifiers. Add. Invert for text group influence. No. Check armature. Open envelopes. I don't know. I don't know. I'm gonna have to read the manual, but I'll understand the manual more after I've first been exposed to the completion of the Humane Rigging Blender Foundation training DVD. Oh boy. Oh boy. Four hours. 4 hours working on this well. 4 hours slugging in the rain. 4 hours working to the build and 4 hours till it starts again. Holy.
For Mr. Hot Dog, we're going to put it on the IK hand control. We're going to name this FK_IK. The order here is important because I want the FK to indicate the side of the slider, that means FK, and IK to indicate the side of the slider, that means IK. In this case, left is FK and right is IK. And make sure it has a min and max of 0 and 1. Now let's move the IK hand so that we'll be able to tell when our switch is working. And copy the RNA path of the custom property so we can paste it later on. Select the upper arm on the intermediate chain, and add a driver to the second constraint's influence. Now configure the driver to use the custom property. And let's try it out. Yay, it works! Now we just have to copy the driver to the forearm and hand constraints. Now when we use the slider... Woohoo! Awesome! Finally, let's move all the arm bones that the animator won't be using to a hidden layer. And let's move the FK and IK controls to separate layers. And put the arm bones back into the same overlapping position in edit mode. Now we can seamlessly use both the IK and FK controls. And of course, let's make sure that it's all working with the root bone. Yep. Now, now, as always, I'm going to go and do this for the other arm off screen. All we have left now is the fingers and the eyes.
Oh boy.
So close. Let's do the fingers next. The first thing we're going to want to do is set all of the rotation modes to the appropriate Euler rotation order. We're going to use the same rotation order as in the finger video, Y, Z, X. Let's do this on both sides of the character. If you recall, we'll be doing the finger rigs with action constraints. One of the cool things about action constraints is that you can use the same action from multiple action constraints. Therefore, we really only need to make a single action that has every finger in the rig bending, and we can use it for all of the finger rigs. So let's do that. Go ahead and key all of the unbent fingers on frame 1. Then switch to frame 11 and bend all of them. And key all of them in the bent position. Now scrub the timeline to make sure we did it right. Excellent. Now let's go to the action editor. Remember that it's part of the dope sheet. Let's name the action Finger Bend. And set all of its keys to linear interpolation. And finally, let's remove the action from the armature. The fingers are still bent. What happened? What happened is that we removed the action when we were on a frame with the fingers bent. And when you remove an action, the current pose still remains. It's just not animated anymore. To fix this, simply select all the fingers and clear rotation. Now let's create one of the finger rigs. I'll just do one and then I'll do the rest off screen. It's the exact same process for all of them. First, we need to create the control bone. It's important that the control have the same parent as the finger. After all, if the hand moves, you kind of want the finger controls to go with it. In this case, since I duplicated the finger's first bone to create the control, I know that they both have the same parent. Now scale the control out to be a bit longer than the finger, and name it. Add the action constraint to the finger bone. And configure it. And let's test it. It works! Yay! Now copy the constraint to the tip of the finger. And constrain the rotation of the base of the finger to the control. And let's test this. Yay, it works! However, there is one little thing that I didn't mention in the finger tutorial, because it's easier to demonstrate on a full rig like this. Try scaling the root bone down, and watch the finger while you do it. You'll notice that the finger is bending. That's because right now, the action constraint is triggered based on the world space scale of the finger control bone. Scale down, it scales down too, and therefore the finger bends. But that's not what we want. Fortunately, we can just change the action constraints to use local space. Now when we scale the root bone down, the finger stays put, because now the constraint only cares about the local scaling of the control. In most cases, this probably isn't actually that critical, but especially for a cartoony rig, the animator might want to scale the character's hand for some reason, and we don't want the fingers suddenly bending when they do that. Now we just need to move the control back into place. And unlock the transforms of the control. And we're done. Now, if you'll allow me to rig the rest of the fingers, I'll be back in a jiffy. We're almost done with the actual rigging. We just need to do the eyes now, and then a few polish items. For starters with the eyes, let's just set this up the same way we did for Mr. Squeegee Feet.
Okay. My brain is really getting fried. It's been... Oh boy. The... I'm lost. I don't know how I'm supposed to apply it to the rig that I already have. But I am in fact lost. Vertex group. Vertex all. Physics, particles, modifiers, and envelopes, constraints, data. Assign selected to active vertex group. Assign. Selection sets. Bone. Oh. Oh. Oh no. Oh no. Um. empty groups. So this modifiers display modifier and edit. Display modifier and edit mode. Edit mode. I don't even know where to begin. Okay, okay. Back to first principles. Animation. We did most of the humane rigging. Animation editors. That's a set of editors designed for creating, editing, and finding animation. Dope sheet, the graph editor, nonlinear animation editor, drivers editor, movie clip editor, video sequence editor. Together, these editors are backbone of Blender's animation system. Quick keyframe adjustment to advanced rigging, motion editing, visual effects integration. Playhead. Scrubbing area. Top. Shift right mouse button. To basic usage, basic rig generation. Add a meta rig from the add armature menu. Edit bone positions to match character geometry. Okay. I'm getting. Oh, my eyes are just glazing over and not even reading the words. Oh man. Anything worthwhile is difficult. Anything worthwhile is difficult. It's been 4.5 hours. I'm thinking that I may need a break. And that's okay. It's okay to have breaks. I have to constantly remind myself of that. It's okay to have breaks. Okay. I'll start streaming at some point. I need to figure out a schedule. I can do like an hour or two before work every morning. That looks like it's also going to give me a little bit of burnout. I'll figure it out. I'll figure it out at some point. I'll see everybody later. Bye.